Good afternoon, everybody. So after lunch, the second tutorial of the day. Faster Python programs measure, don't guess. This is the tutorial. If it's not your tutorial, you have to change rooms. So again, please make sure to install all the required software and also download the material. First, I would like to introduce myself a little bit. So I've been a Python user for now about 20 years. I remember buying my first Python book in 1999, or Python 1.52. It's a bit newer now. And also work as a Python trainer since 2004. I've trained people in Python. And actually since 2006 I do it full-time, and I'm the CEO of Python Academy, though we're a Germany-based teaching company, so I teach in Germany and other countries in Europe. I'm also involved in the community, so I've been chair of a bunch of Python conferences you can see here, and I'm still involved in organizing PyCon.de and EuroSciPy and maybe some other conferences. And also the chair of the Python Software Verband, which is something similar to the PSF, but a bit smaller and in Germany. Okay, maybe a few words about you. So there's quite a few people in the room, and it would be good to have a little bit of feedback who you are, what you know about Python. So who has less than 1 year of Python experience? Please raise your hand. Okay, it's about 10%. Between 1 and 2 years? Okay. Between 2 and 5? Yeah. And more than 5? Good. So it's a pretty nice kind of even distribution with different, of course, with the time of the usage of Python is not a good measure, but it's some kind of approximation how well you know Python. So who of you has to still use Python 2 in production or for their job or something? Okay, still quite a few people. So this tutorial, I've been using this for a while, so I updated it, but it works with Python 3 and also with Python 2 mainly. So you should be able to get something out even if you have to still work with Python 2. But remember, end of the year, Python 2 is dead. So we probably should speed up a little bit the moving from Python 2 to Python 3. So who of you is doing number crunching or something that has to do with numerical computations or something? Okay, a few people. Who of you has CPU-bound problems, more or less? Yeah, okay. Who has more memory-bound problems? Okay, so there's also this distribution. And who has more I/O-bound problems? Okay, so kind of even distribution, all kind of problems are here. Good, thank you. What are you going to do? So we have about 3 hours here, and this will be hands-on. So I just have a few slides, and then we I do kind of live coding more or less, and you're encouraged to work along. Then you can also go to the material. Everything it's in the material, so hopefully you won't get lost. You can do copy-paste, but typically it's not that efficient, so it's not too much to type, and maybe try to type along. I'm going to use IPython notebooks. Actually, it's called Jupyter notebooks. Who of you is familiar with Jupyter? Most of the people. So I will give you a very short introduction. If you want to use some different tool, you can use some different tool. But a few things, some timing and profiling things work much nicer than in notebooks than if you don't know this. You have a handout. There's about 78 pages PDF handout in the download. Also example code is also downloaded. We do some exercises a little bit, so you have to do something yourself, not a lot, a little bit. And there will be a break at 3 o'clock, so there will be some new coffee, hopefully. And also, you can go to this link there after the tutorial and give your evaluation how you liked it or not, or didn't like it, some suggestions or something that would be nice. I will show the link again. It's here. And maybe I also, during the break, I uploaded that you can have it, just you click it, you don't have to type it in. Okay, so first a few words introduction, because everything is about making things fast in some way. So as you know, Python is a pretty high-level language, very interesting language actually, that makes programming easier, but Python can be slow. Python's not necessarily slow per se, I would say, but for few things, it can be slow. Typically, it's really slow if you do heavy numerical calculations in pure Python. That's not going to work out well, but there are quite a few solutions to do it in a different way. We're going to look at some of them. This may or might not be a problem. Sometimes it doesn't really matter too much. So if you program something and you're waiting for something like a database or so, then there might not be a problem with Python at all. And before you start optimizing to try to make Python faster, very often it comes with a cost. So you have to pay for it in one way or the other very often, and you're going to look at this a little bit. Because once you optimize the code, you might need to spend more effort not only writing the code, but also maintaining the code. It's more complicated. So you need to find some kind of a balance. And of course, this is very different for each application. Sometimes if performance is very important, then it makes sense to do it. Sometimes it's not so important, it might not make sense to do anything at all. So optimization guidelines, premature optimization is the root of all evil. You might know this. It's not really clear who came up with this the first time, to say Hori, but maybe somebody else. But it doesn't really matter too much, or Knuth. But this has something true. I have a lot of people, sometimes I work with people that say we have to use Fortran to program this because otherwise it would be slow. That might be a little bit hasty decision. Very often you might need Fortran for only a very small portion of the program, actually, not for the whole thing. And then you have to write the whole thing in Fortran. That might not be the best choice for some problems. Very often you have to make it correct first and fast later. So it doesn't make sense. You have a very nice fast program, but the result is not what you want. So you have to make sure the program works correctly. And you can also think before you start about optimization, but it's typically a very bad idea to optimize on the way. First, you have to make it work right, have tests, and then once you have the tests, you know the test works right, then you can make it fast. That's a typical way to do. So correct before fast. So otherwise, you might not be very successful. So, as I said, optimization often comes with a price. It can make your code less readable. There are other cases where the code actually gets more Pythonic, as you might call it, and more readable. And I try to show you some of these sweet spots where the code gets easier to read, better to understand, simpler in one way or the other, and still faster. But sometimes that's not possible. And you might end up putting more effort in maintenance of your code. The readability, which is a big feature of Python code typically, may suffer if you put something in there that makes it faster, but not as nice and Pythonic maybe. Because Python typically puts a load on the machine and not so much on the programmer. And if you reverse this process a little bit, then you might lose some of the advantages of Python. And sometimes you have this kind of different thing, and then you have to find some kind of compromise between these different goals that are not, you cannot solve for both of them. So, general guidelines. So I have to this is pretty much common sense, but even though it's common sense, you have to just keep this guideline somewhere when you do optimization before you spend a lot of effort, just go through there. And then, of course, you have to apply this common sense to your actual use case, which is different pretty much every time. So do you really need, it's a kind of strange question, do you really need more performance? Maybe you don't need it. It's just an exercise to do something faster. It can be okay, but maybe you don't actually need to make it faster. Also, you have to figure out if Python is actually the cause. And that's pretty much most of the tutorials actually figuring out what's going on. And this is a very, very important basic step, which is rather general, to find out what the problem is. Then how to really solve it, that's something I cannot really teach too well in the tutorial because pretty much every case is somehow different. But if you have some general guidelines, then you can apply them to your special case. So there might be other things, network traffic, whatever, that are slowing down. It's not Python. So I always say it doesn't matter if you wait fast or slow, you still wait. It doesn't help if you may use C or some other fast language when you don't have anything to do. And does it hurt if your program runs slowly? If something runs 2 hours or 6 hours and it runs overnight anyway and is finished in the morning, it might not matter. So this is something you have to answer yourself. So as I said, don't optimize as you go. So you have to make it work right first and then look at the speed later on, because you very often don't know if this really matters what you're doing right now. And so you have to measure. That's something I will hammer on quite a bit. And I do this for a while and have some experience, but very often I'm wrong. I have an assumption what it is, but when I measure, it's wrong. In the aftermath, it's very clear, but when you start, you very often have wrong assumptions, and that can happen. Use realistic use cases. So what is a program for? Yeah? So if something runs overnight, then you don't have to make it very interactive typically. So how many people are going to use it? So if you know you're a small company and you only have 10 people, there will never be more. You don't have to scale up to 1,000. Yeah? So sometimes it's very difficult to predict how this thing is going to develop in the future, but just spending a lot of effort for something that might never happen, maybe not a good idea. Yeah, how often it's used? This is a one-time thing, and then you throw it away. Then it doesn't make a lot of sense to spend a lot of time to make it faster. Yeah, because you just wait till it's finished and that's it. So again, external causes can be typical candidates like network connections. Everything goes to the network can be much slower than anything you do in the programming language. So you have to check this one. Database access is a typical case. System functions. You might find some other things depending on your use case. There can be other external sources that make your program slow. Architecture. So architecture can be thought of a kind of a higher level algorithm. Like how do you set up the whole thing? Maybe you have a flaw on the whole idea you have. This is really difficult to tell. And I don't have example because typically it's like the bigger picture. And typical simple tools work. So if you have a big piece of paper and write boxes and arrows and see how they work out, and if they all cross each other, then it's typically a sign something is wrong. Yeah? Most of the time, simple tools are good to give you an idea. Complicated tools are not necessarily better. Sometimes you need them, but something like just to have a general picture how your program is set up, and maybe there's a problem somewhere in there. So, general rule. Bugs, yeah? Forgotten to print in the inner loop. Or something like this that slows your thing down. So print can be very slow, especially in Windows. If you have a print on a console, that's much slower on Linux typically. And debug might be the problem. So if you make your program work right, then you might not have a speed problem in the first case. Yeah. So, and now, once you're through these 6 steps, step number 7, now you say, okay, I have a case. It's too slow, I have to make it fast. Very often, not the whole programmer is slow. Typically, you have some bottlenecks. Actually, hopefully, you have some bottlenecks. If really everything is equally slow, it's really hard to make it faster. But fortunately, in many cases, you have 1 or 2 or 3 bottlenecks somewhere, and you have to find them. Yeah, you have to find them where they are, and then you can focus on these bottlenecks. And that's what we're actually doing here. We're finding the bottleneck, and if it's your domain, you know what's going on. Maybe if you found the bottleneck, it's very clear how to solve it. Maybe you cannot solve the bottleneck because you have to do these computations anyway, or something. And it's very different for each use case, but very often you have bottlenecks, and sometimes they're even easy to solve. But of course, you need to check after your optimization if it makes things faster, if you still have the same result. Yeah. So use unit tests. PyTest is a framework. There has been a talk here, a tutorial about PyTest, which is highly recommended because it makes it very easy to get started with tests actually, but gives you a lot of sophisticated features later on. So it grows with you, and you should try to cover most of your code. So even if you have 100% coverage, it's not a guarantee that your program is correct, but it's one more indicator that things are going well. And then a rule go for the algorithm first. So if you apply the right algorithm, you can, if you have a certain problem, easily speed up your program by many orders of magnitude. No switch of programming languages can do this. So if you switch from Python to C, you can get a speed up between 10 and 100, depending what type of thing you solve. That's probably what he can do. So a lot of numerical code, he can be up to 100 times faster with highly optimized compiled code. But if you use a different algorithm, and Python has advantage, it comes with data structures that have very powerful algorithms behind it, and if you use the right one, you can be 10,000 times, 100,000 times, 1,000,000 times faster. No compiler will give you this one. So this is something you can do. Actually, I gave a talk in 2012 at EuroPython. I said Python's fastest in Fortran, which is a kind of a provocative title. And I just did something like we have 2 files with 1,000,000 coordinates, X, Y, Z, and find out which ones are those. And in Python, it's a 9-line program. Open both files, read them into sets, do an intersection, write it out, everything. I tried to reprogram this in Fortran. Took me 168 lines. And I couldn't find anything like a set in Python. And I made a naive quadratic algorithm. And the Python program ran like 2 minutes, and Fortran took 2 hours. Of course, you can say you do a binary search, but if you do binary search in Fortran, that will take you a few days to program it and get it correct. In Python, I can do this in half an hour or a few minutes, actually, the whole program. So if you have the right algorithm and you take advantage of Python built-in structures, that can make your things faster. And as strange as it sounds, sometimes it's just the easiest way to throw hardware on the problem. So nowadays hardware is really cheap compared to programmer time, and maybe just put more memory in. So putting more memory in is always, most of the time it's possible, and putting memory in is pretty cheap comparable. Getting a faster CPU, it's, you can get many CPUs, many cores, but of course then you have to change your program that it can take advantage of it, and Python has some problems with that sometimes. Some libraries do this, but if it's a memory problem or some input-output problem, just replacing a hard drive by SSD or something might be very useful already. Yeah, and of course you can, whatever you can buy, that's typically cheaper than optimizing. Of course, if you have something simple to do and change the algorithm, that's still, we can still do it on top of it, but more hardware will help. Good, that's my slides. Now, let's go and do some work here. So I'm going now go through some examples, and we work with the Jupyter Notebook. So I created a new environment here. You don't have to do this, but if you're familiar with Conda or some other, or if you can use pip virtual amps or something, whatever you feel comfortable is fine. Or if you work in your main environment, I use Python 3.7 here for the tutorial. If you have a question about 2, so it should work with 2. Yeah, a few things might be slightly different, but for the most part, it should work with 2. And I activate it when I install the software. And actually now I'm starting a Jupyter lab here, and I need to specify a port here, otherwise it's not gonna, something like this, see if this works. And then it should start a Jupyter Notebook in this directory, and that's what it does. So, and I made a mistake. I have to go to the directory first, because otherwise it's always recommended to go to this directory first. So, and then to do the same thing again. Then all the notebooks will be automatically stored in this directory, and I can get rid of this one. So it worked. Now, I have a problem is I have to use a different port for some reason. Use a different port. It has something complaints about workspace if I use the same port. You didn't kill the one. Okay, so this is actually the download, the examples, and I make a new notebook, and I will spend most of my time in the notebook, and typically I rename it. So if you want to use some other tools, that's fine. The advantage here, I will develop this notebook and I will upload the notebooks, and you will get the link to the notebooks. I'll send them out. Later on you get all my notebooks, because yours might look a bit different. So I don't have any prefabricated notebooks. You have the handout, it's a PDF, so you have all the information there, but I don't want to just show you something, you have to press Shift-Enter, Shift-Enter. This is not typically a good way of doing it, because you want to do something yourself, and therefore we spend some time in the notebook. So is this big enough? Everybody in the back can read this? Yeah, okay, great. So let's go through. So I'm pretty much following the material. Of course, you're always free to ask questions, so raise your hand, and if I don't look at it, just make some noise. And you can always ask questions, either answer directly or just say, okay, we will going to cover this later. We start with measuring. So most of this tutorial will be about measuring, and then I have, in the second part, some hints looking at some algorithmic things and some suggestions what you can do. Since there are many different types of problems in terms of performance, I cannot cover all of them, but I can give you some suggestions. But the main thing is you need to measure. And once you measure, you might solve your problem already. If not, at least you have something, then you know, I could solve it, I could not. Was it time worth it spending it? Okay, the first thing is timing. So timing can be done in different ways. There's a library called timeit, which is part of the standard library in Python. So you can import timeit. So this has advantages always there, but it's not really comfortable to use. I would say it's not too bad, but we'll see there will be a more comfortable way here in the notebook. But let's do this. So I can do something. I just use my example. So I define two variables, a and b, yeah, and I just want to measure how long it takes to add a and b. And to do this, I can say total time, yeah, and I can use a time it module which offers you something. So measuring time is always kind of tricky. Can be pretty tricky. That's why you should use tools. For those people that develop the tools, they thought through and they try to make it robust in one way or the other. There can still be problems, so you can still measure something strange. And now I can say measure A plus B. So I use a string. So I have to have a string. And then I have to specify a few things, like I say the global namespace is, I can say locals and globals here in my notebook is the same. So I can use locals and I can supply this namespace. So now that defined A and B end up in locals in the dictionary and feed this dictionary there. And I can say, I can specify how many times I want to repeat it. And if I want to have 1,000,000 times, so I'm Python 3, I can do something like this, if you might know. So you can do underscore, that's easy to read for 1,000,000. In Python 2 you cannot, you have to type it out or do something else to get to your 1,000,000. And once I do this, and then I can look at the total time, and I get the total time in seconds. So it took 0.063 seconds about to do 100 million loops, and of course now I have to divide it, and that's why actually what I said here, I can say repeat if you want, and then you don't have to repeat, so to speak. So 1,000,000, and you use the repeat there, and then you have to divide the time by the repeat. So, and then you get the time for one. Yeah. So now the total time for one run is about this much. So this is the time, but when you're in the IPython notebook or on the Jupyter notebook, you can actually use this magic command. This notebook has this magic command. The %time it is not a Python thing. This is a Jupyter notebook thing, and I can do the same thing here, and I can say A plus B, and then it's using time it. It's actually using this machinery in the background, but it gives you a much nicer interface. You will see this because you don't have to do a lot of things yourself. And now it tells me it takes 45 nanoseconds to do this. Yeah. So nanoseconds 10 to the minus 9 is about 5 times minus 8, which is about the same time. It's the same result. But you see what it did? It came up with a number of repeats itself. And the number of repeats, actually, if you check here, it's about 10 million, if I'm not mistaken here. Yeah? So it repeats it 10 million times. And it divides the time by 10 million, obviously. And then it does some statistics. It repeats the whole process 7 times, 7 runs, and then gives you the mean and the standard deviation. So this is good because if the standard deviation is small compared to your measurement, then you say, okay, you have 7 times pretty much the same result. And this is useful. If the standard deviation is big, you have a problem with something, caching or some kind of thing. Yeah. So this is some indication. Again, there's nothing 100%. When you measure something, you always make mistakes. Just the question how big they are. Are they 3% or 300%? That's the thing. So 3% it's typically okay, so it won't be that picky. But 300% is obviously not okay. Then you have to do something with the measurement. Maybe you cannot do anything because you have so many moving parts, and every time you measure, everything is different or so. That can happen, but this is one way to measure the time, and you can do this. So we can also say %time it 1. So you see 1 plus 2, yeah. So you can use literals, and you see when I use literals instead of A and B as names of my objects. So typically I don't say variables, I say objects. And you see now the time goes down to about 9 nanoseconds, which is more than 4 times as fast. Here I can still calculate, but you can actually use a small, actually if you say time it question mark, then you get the help. And you see this time it takes several arguments. You see there's a time it with 1%, and there's a time it with 2%. 1% is just valid for one line. The 2% will be valid for the whole cell. The cell is this gray thing here. Yeah? And you can have several options. You can determine, if you don't like this automatic calculation, how many repeats you want. You can say, I want to have 10 repeats, 10 million, whatever, many repeats, and so on. All these things can be used here. And one of the interesting one is O, and this dash O here returns a time result instance. And we want to do this because this time result instance has way more information than just what is printed out, and is as Python objects. You can access them later on. So if I say this one is pretty useful, so I like it. So I say dash O, lowercase o, a plus b. And now this returns this object, and I can retrieve this object as a time with, okay, let's call it variables. I use variables here. This would be this time. And I can do the same thing as a time literals. So if I type in my literals, time it, O 1 plus 2, you see. Now, you still get the output. You can suppress the output if you don't like it. Actually, there's another switch for this. But now you get the output. Then this output does have several attributes. You see, type, you get all these attributes. And the interesting one is average. And average is exactly the same we just saw here, just not in nanoseconds, but in seconds. And now I can do an easy calculation. This is kind of okay, but if you have different units, you always have to calculate in your head with the units or do something like this. So this is typically nicer to do something here, and you have average, and you see the factor is about 5. I said 4, more than 4, but it's about close to 5 in this case. So if you repeat the whole thing, you will get slightly different. Yeah.
One question. It happened in the last class too, but with the magic time it with the percent sign, mine doesn't show the standard deviation on there, and I'm wondering if
Yeah, so are you sure you have the same version? So if you say import IPython and then check the IPython version, so that might be something because the older version, do you have 7 repeats or 3 repeats? Yeah, best of that, then you have an older version. So there used to be best of 3, and a few versions back, they changed it to 7 repeats, and then they also have the standard deviation. So if you typically, the version, as you know in Python, typically, it's not there. There's a version. So you can just go and check up here, help about Jupyter Lab, and then you see the version, and this is a version 0.35. Maybe the IPython version. Maybe figure out the versions. I'm not very sure where the version is right now. But if it says only 3 repeats, then you have an older version. You have like 3 or 4 versions back or something like this. This is an IPython feature because Jupyter Lab has several parts. But I'm surprised if you install the newest version of Jupyter Lab, it should actually get the newest version of the IPython also because it's a dependency. Maybe for some reason it doesn't work. Maybe they have some configuration options or they set it back or so. There's a lot of configuration things you can do with here. So, but if you make a new install and try it again, everything clean sheet, and try it from the beginning to see if it works. So I'm not sure where the version is here, but it looks like an older version to me. Okay, the 2% sign, as I said, you can use this one. Now I can say A equals 1 and B equals 2. If you stay with our simple example, say A plus B. And now it's measuring the whole cell. So it's measuring the assignment as well as the addition. Yeah. If you don't like this, if you don't want to measure the assignment, you can actually move this assignment in the first line and make it a precondition which is not measured. Here we have to use a semicolon. Actually, yes, because we want to have 2 lines there. So now, if you do this now, it doesn't measure the assignment. It should be hopefully a bit faster. Yeah, it is faster. Yeah. So assignment is not expensive compared to this resolving with the names. But it gives you some clue how things are. It's sometimes interesting to get a feeling. So if you have a different machine, a different operating system, you might get different readings a little bit. Yeah, so good. This is the first thing. Timing can be interesting, and using this notebook is very nice because the overhead doing it, the effort is pretty low. You don't have to do much, and very quickly just check, is there a difference if you do it this way or this way? And if it's pretty much the same, it doesn't matter too much, at least for my use case. So all this timing and profiling can depend on many things. And one big thing is like the size of the data structure you use. If something works for a small data structure, it might be very different for a bigger data structure. And what small and big is depends also on the machine, on the CPU you have, and caches, and all kind of stuff. Yeah. So if you do measure, you always need to measure for something that's kind of more or less realistic. If you just use a list with 3 elements, also, always you don't see any difference in looking up in a list. If you have 3 million elements, it might be very different, or 300 million. I might be very different. Okay, this is, so actually I can here develop my notebook. The first one, this is, I can use Markdown. You see, I changed the cell to a Markdown cell up here, and now I can use Markdown and then do Markdown. So how did I insert a cell? Escape A and Escape B. So if you haven't used the notebook yet, you can open this site here, and then you go to this, the palette, which gives you help, and you see a lot of these help things. You can even search them, and some of them have keyboard shortcuts. And if you do things often, then you should keyboard. This is a Control B to turning off this left pane, on and off the left pane. And these are here. If you press Escape on one of them, then you can draw the cell. Yeah, so if you say Escape 1, I make a cell, a Markdown cell with header 1. If you say Escape 6, it puts 6 of these hashtags in there to make it. So this makes it easier. Yeah, and also here's my insert. Yeah? We can also delete a cell. Yeah, since the deletions you destruct the cell, they have to repeat it, DD. So for the user here, and then there's a Escape A somewhere. Must be Escape A here. Insert cell above, and B insert cell below. These are pretty common. Good. That's what I did here. And if I turn this off, then you get more screen real estate and see more. So the next thing would be actually profiling. So far we just time something, and timing you can only time a whole thing, and that's it. That's it pretty much. And here I can say profiling, and profiling means looking deeper inside. So profiling is if you have a program that's a bit bigger, and you want to find out which part is actually consumes how much time. So this is now CPU profiling. Later on we'll do memory profiling, which can be even more complicated. Memory is not that easy typically, and there are no built-in tools. Here in profiling we can use some Python standard library tools. We'll see there are some other external libraries on top of it that use information the profiler gives you to give you nice graphics and something, which is typically helpful. Yeah. You can also, if you will, find some other tools if you have other machines, but the principle should be the same. You need to measure something. And also, once you do profiling, you might want to automate this profiling in the way that fits your project. So that's typically useful to automate things here. Okay, so if I say, actually the percent, ls is nicer to do. I have this subdirectories from the download, and if you go to measuring, then you will find, yeah, so this is from the download, the zip file. Did everybody download the zip file? Yeah, good. Good. So there's a few things in here. Typically, it's very, very small programs. You could type them in, but it takes too much time. And they're all toy example programs. But I try to make them as simple as possible, but still to make the point how to do it. Of course, in reality, this will be way more complicated, but then it will be kind of disturbing what you're doing. So I can load this here, so you can open an editor if you like, but you can also open it here. Profile me. You see, when I start typing, it gives me call tips. It loads a file, and this is a very simple file. So I still have some Pureman's Python 2's Python 3 compatibility in here. So Python, of course, it's important to use the Python 3 type of range. In Python 2, you have X range. It's not exactly the same, but for our purposes, okay. So Python 3 range can do things like you can use a long in range. X range is limited to 64-bit integers or something like this. There are some small differences, but for our purposes, they don't matter. And I have two very simple functions. I use the built-in function time, a built-in module time, sorry, and use sleep. So this sets your processor to sleep for that many seconds. That typically tells operating system, please wake me up after this time. Yeah? You have to be careful with sleep. Sleep is not very accurate. Especially in Windows, it's very inaccurate. So if you sleep a million times, in millions of a second, you end up not with 1 second, but with 10 seconds or something. That's totally off. Yeah.
Sorry, I think I missed the command to get this.
Yeah, so I go up again. So always raise your hand, I'm too fast, because so I unzip the file, and in the directory measuring, there's this ls gives you all the files, and then I use %load, which is gone. So actually I type %load and then the file name, yeah, profile me, and when I execute it, it will turn my command into a comment. Yeah. So if you go to the schedule and to the notes, and if you're logged in, you will see the link there. I sent a message last night, and there should be the zip file. Yeah, so then the zip file can download from there. But you have to be logged in, otherwise you won't see it, because you have to be. But since you're registered, you should be there. Otherwise, you wouldn't get registered in the first place. Good. So this is a file, and there are some very simple functions. So this is actually Python 2, Python 3 compatibility. If you're on Python 3 or Python 4, so not there yet, it won't have any effect. Then there are two functions. This waits at a thousandth of a second, and this waits at a tenth of a second. Yeah. So there's two small functions, and then there's two more functions that use this function a loop. So I repeat something 100 times, and since I don't use a loop variable here, you could use X or something, use underscore, which is typically a pattern in Python to do. If you want to have an anonymous name, so to speak, which is kind of strange, oxymoron, then use underscore typically. And I just repeat it 100 times and see what happens. So this is just a very simple example. It doesn't do anything useful, it just waits so many seconds. So if I actually execute it, it takes a while, because now if I wait 100 times a tenth of a second, it takes about 10 seconds. So it should take about 10 seconds. After 10 seconds, you should see that it returns. So as soon as the number is here, then it should have returned. Good. And now I can profile things. First, I'll show you the slow way to do with a Python standard library modules. So I say import C profile. So this module has a name which is not supposed to have. So according to PEP 8 naming guidelines, it should be all lowercase, but the capital A P made it from Python 2 to Python 3 for some reason, I don't know why. But in there, so it's supposed to be lowercase, but you have to type it. Even on Windows, yeah, because Windows is not case sensitive, but case preserving. Even in Windows, you have to type the right case, otherwise you're going to find the module. It's kind of strange. Good. And so I make a profiler, so I make an instance of a class. So it's the long-winded way of doing this. So I say module C profile dot class profile, and I make an instance of this class. And then this instance provides a few methods, and I use one of them. It's called run call, and then I feed my function, and I can give it the arguments. Since it doesn't take any arguments, I just give it a function without anything. So I don't call the function. It's a callback. I give this thing my function. It's calling the function on my behalf, and this is very fast. And then I say profiler dot print stats, and then it prints the statistics. It looks like something like this. I have to make it a bit shorter so I don't get line breaks. Hope it's still readable. So this is a very simple statistic. This is very simple. You see, it's just 4 function calls. In reality, there can be hundreds and thousands of calls in your program if you run a function under this profiler. And you get an output. And you see, there are 202 function calls in 0.12 seconds. And this here is the number of calls, the total time that are spent here, the time per call, which is, since it's very fast, is 0 here, you don't see much. And then the cumulative time here at this one. And then actually the time per call. Yeah? So this is the cumulative time of the outermost function is the total time. This is this time up here, obviously. And then the other one is the time accumulated. And you see this is here a function that lives in the notebook, has a strange kind of name here. This is a file name. And I use fast first from outside. It's called once, which calls fast 100 times. That's you see the 100 here. And fast actually calls the time sleep method in turn. And of course, the profiler measures the self. Yeah, so this always, when you measure something, the tool measures itself typically. You cannot get away. It's like you have this thing, if you're in a room and count the people, you count yourself, or something like this, some kind of strange thing. But this can happen that the measuring has an overhead and somehow impacts the measurement. It's kind of unavoidable, but if the impact is small, it's okay. If the impact is the main thing compared to a measurement, then it might be a problem. So typically, measuring something very fast is much more difficult than measuring something long. If something takes 10 seconds, it doesn't matter my overhead. 10 seconds. If something takes 1 nanosecond, then my measurement consumes 10 or 20 nanoseconds, then there can be a big problem because I might measure something that's not there. I measure some kind of a ghost effect. And then if you try to make a ghost effect going faster, you won't be very successful. Those things can happen. So now you can do a lot of things with this profiler and can get, so actually I can use the same, I can make a new instance or can use the same instance. So I can use the same instance or make a new, I can make a new instance, profiler 2 here, and do the same thing, make a new instance. See profile, capitalized profile. And now I can just do the same game again with my profiler 2, run call, and of course now I use my run slow, and then you will see, use slow, and then run call. So run takes a string, run call takes a function. So there are different ways of doing this. And of course it takes longer now. That takes my 10 seconds, so I have to wait 10 seconds to see a result. And then we need to do the same thing as here. Instead of profile log, we say profiler 2, and then we see the output of this call. And you see, I called run, that's why there's one more call there, I guess. And then you see the time it's spent in sleep. And the sleep time is now 10 seconds versus this 0.1 second. Yeah? So yeah, you have to load this file and then go in there, press Shift Enter, otherwise it's not executed. So if you load it, it doesn't execute for security reasons. You have to look at the file, just code first, and then go in there, Shift Enter, otherwise it's not defined. You can also import, it's the same directory, you can import it and use the import, normal Python import, that's also fine. Good, so now you see the difference, and here's very obvious, sleep takes all the time, and we have to do something about the sleep if you want to make it faster. Yeah? Here, threads would help, yeah? Because sleep is input-output, and you can use threads, and it would go away, so to speak, if you wanted to. Yeah? So when you have input-output, and you have a clear case, threads are not too bad, actually. If you don't use any shared objects and any locking and so on, threads are fine, I would say. If you have shared objects, threads are typically not recommended. You might find a better way. So this is input-output bound here, and the sleep takes a time. And if you know a little bit about sleep, then you will solve the problem. Yes?
What is the built-in spec check? I don't have that in my output. Maybe I have a different version, but what is that? The built-in spec check? The method? There is one called it.
Which method?
The third one.
Yeah, this one? Yeah, this is a measurement itself.
The third one. Built-in. The one in the middle. The built-in spec check.
Yeah. This because I used run up here first before I used run call, and run uses a string and it calls the exec. That's why also I don't have 202 runs, I have 204 calls. Yeah. So actually, if I want to do this, that would be a trick, because I now have some artifacts that are still in memory but don't show up in the notebook. I deleted the run to call, but the effect is still there. So trick, it takes a while, but I can say kernel restart run all cells, which now would restart my kernel and does all these things from the beginning again, and reruns all my cells. Does it do it? Did I say yes? So you say kernel, restart, run all cells, restart. And it doesn't do it? And now it does it. Okay. I did it. And now you see, now I have to wait here. Because now it takes so many seconds, I have to go to the whole game again. We have to wait a minute or so. But then this would be a thing now, you would delete everything in memory that's there you don't see anymore. You can still access it, but this would be just wait this while, let everything restart and do all these things. But I have all this timing in here, so it's now doing all this timing. We have to wait 7 seconds, 7 seconds, 7 seconds, and it's recalculating. So the star means it's busy doing something, and now it's doing this one here. So it's still busy, and then once everything is through, here we have 202 here. I should see 202. Yeah, actually it's 202 now. So this is a fast one, and this is now it's 202. Now it's done. Yeah, you see, instead of 204, now the exec is gone because the run call is not there anymore. This can happen if you work interactively, you do something, you delete the cell, you don't see it, you forgot that you did it, but the effect is still there and you measure the effect in one way or the other. So always make small notebooks. If something is strange, restart the whole thing, do it new. So otherwise, figuring out what happened, it's not worth it, just redo it, yeah, very often, yeah. You remember this, so if it doesn't have effect, you change the file, just to remember there's two files with the same name in two different directories. Those kind of things happen, and then you have to make a step back, go drink your coffee, and come back, and then you have the solution that you do something strange here. Good. Now we have this statistics, and then you can do a lot of with the statistics and work with it. So you can sort it, you can limit the printing, and so on. There's a lot of these output things. You can also actually do the following. You can say C profile dot run. Yeah, and now run would take a string, and the string uses exec. So you type in the Python source code that actually is supposed to run. So I can say use fast, and actually call use fast here. So I type the code in literally, and then I can also say if I would like to store this. So I say fast.stats, and this stores the result. And I did something wrong. Yeah, this is a file name. Yeah. So now it runs it through, and then you have this this file in your file system. This is a binary file, so it's I think I use Marshall or some kind of persistent thing, but it's standardized, and a lot of tools will be able to read this. So you can do this profiling in your code somewhere, and then post-mortem can go through the results. And this is a kind of standardized format, and there are quite a few tools that are able to read it and do something with it. Yeah, so you can write your own tools if you want to. Yeah, so you can put some decorators in somewhere that actually save these files for different versions and so on. Yeah.
So where are these statistics being reported from? You're running in a browser environment, but...
Yeah, so the notebook saves everything in the directory I started from. The current, I can also change the directory, but it saves, the notebook saves everything in my current working directory.
So these are statistics from the CPU and not the app. So these statistics, the profiling statistics, these are the CPU.
This is exactly this numbers actually are stored there. These numbers a bit more. This information about CPU profiling. Yeah. So if you do memory profiling later, there's no built-in module in the standard library that does memory profiling, to my knowledge. I couldn't find any. So we have to use third-party libraries to do memory profiling. So you can measure the memory of one object with this get size of, but that's pretty much it. Yeah.
Can C profile take the average of multiple runs like timing?
As far as I know, you have to do it yourself, I think. So you have to run it yourself, and then you can write some tooling around it. You will see we use prun. The next one is one of the notebook tools that gives you much more higher level and much less effort approach to do these things. Okay, now you can do some more things. You can sort it. So you can say, so my statistics import a tool that's also part of the standard library. Pstats, sorry, forgotten, import pstats. So if you have pstats, so pstats is, as you can see here, this is part of the standard library. I'm using Miniconda here, and this is just in the lib Python 3.7 directory, so it's part of Python. There's always a way to figure out what module is it. Is something that's part of Python or so. Now we can do quite a few kind of investigation steps on it. Just a few examples. So I can say stats, and I can read my statistics. Okay, type too fast. Stats equals, and I can say pstats make an instance of the class stats and feed this file fast, the file we just saved, and then it reads the file. So you can do your profiling somewhere, and then the next day you can do the analysis, which can be helpful. So you can also save multiple files for different things somewhere, and then do the analysis later on. Because when you do profiling, you might slow down your program quite a bit. So it might take a while. So if something takes a few minutes already, that might take a few hours or something. And then you don't want to wait all the time. You can do this and then later on analysis. Let it run overnight or something like this. And now stats offers again a lot of things. I just show you a few. You don't need to know all of them, but you can print a lot. a lot of different types of things. And print statistics will do exactly the same we just seen. Yeah, so we just seen this one, we can do this. Of course, now you can sort this, you can select something. So if you want to sort it by, this is sorted by time per default, and you can also say, I would like to sort it by calls. Then you can feed in calls, and then it sorts it by calls. And now you get this, and then you have to say print stats on it. Print stats. And you can also limit the number of lines you want to print. Say only 3, it prints only the first 3 lines. Yeah, so you can limit the number. This is a very short example. If you have a big assembler, might be hundreds and thousands of lines. You don't want to see all of them, and you just see which one is interesting. Yeah. So you can also go through material. So if you cannot follow, you should be able to catch up, go into the PDF. So print stats, print just the way we had. And now there are multiple options to sort this and do some kind of investigations on this one. You can also find out who's calling whom. So there are some things in there. You have to say can stats, print callers. There's callers and callees. So callers in one way, and so who calls fast, and you see okay, that you have this connection here that use fast actually calls fast here in this direction, and the other way around you can say print callees, and then you get the other. Use fast. Yeah, so just ask the question a different way and say use fast, and you get this information out of it. Yeah. Those kind of things, those things you can find out. Okay, this would be doing things with the Python C profiler. Now we're doing it with Jupyter. So Jupyter uses this library in the background, but gives you, again, very similar to %time it a nicer interface. There's no new functionality per se, but everything is much easier to use. And typically, if things are easier to use, you might get people to use it more easily. So use fast. Why doesn't it come? Is it use fast? Ah, yeah. No, it should be there because I used it. Okay, it's just the call tip didn't come. So you see now it's doing this thing. So instead you don't have to make an instance of something and call the method. You say prun use fast, and it's doing this stuff in the background. And gives us the same output here sorted by calls. And you can also give it a lot of options. So if you say prun, so if you don't know what to do, put a question mark, and then you get the very long help. Yeah? Run a statement through Python code profiler. So it's using exactly the same thing we just did, but gives you a nice interface. And again, you have a 1% version for one line and a 2% version for a whole cell. And then there's explanation, and then you have a lot of options what you can do. So if you don't want to have many lines, you can limit how many lines you want to actually display. It also can return this instance of the stats object we just seen. If you have something already, you can use it. You can also sort it by all kinds of things. Yeah, you can say sort it by this key, and then you can provide a key, and it gives you a list of keys. You can sort it by call, and so on. Yeah, so you can sort it by all kinds of criteria here. And you can also save it. Save whatever it's printed, it will be saved in the file, or you can save it with D, which saves this in a different in the binary file version, and you can read it with some tools later on. Yeah. If it's too talkative, you can suppress screen output, and so on. So there's a lot of things you can do here, and it makes it really, really useful. Yeah. So, and you cannot remember all of these, but it's in the help, and a few important ones you have. So I can use my prun. I can use one of these. Yeah. No, prun. I don't know what that's two. Prun, and I say here my stats. Again, and I can now use the option return. Returns this object, and I can say use slow, and I have to call it actually. Now this will take 10 seconds again because we have to wait so long, and I don't think there's a way to speed this up. And then once we have done this, we can look at this object. That's, since I didn't suppress the output, you still see the output, but now we have the stats slow object, which if I use it and say print stats as we did before, then you see this output. Yeah. So you can combine it now with existing tools. If you have something there, then you can put it in, but it makes it easier to work with it. So again, you can use some of the other options. So prun capital T option gives you, writes everything in a file, and I can say stats slow.txt, and I say use slow. So if I say use slow, and I have to wait again, use slow, and now it writes it in, instead of, in addition, I think, in addition to write it to my notebook, it writes it into a file. So you know, if you copy and paste it in the file, it will be in a file. So if I now say ls, you can use the ls without a %, but it's nicer to do it with ls stats slow, and you see it's there, and you can look at it with less, yeah, and you see that exactly the output we have. This would be one option. The other would be doing it instead of a T with a D option. So instead of a T, we use a D option, and now we use our extension stats. So you can make up any extensions, but this would be now the binary version, and then you can load it again as we did before. Good. This is something that can be interesting, it can be useful, and gives you a lot of information and doing things. Good. This would be basic profiling with a profiler here. Now, the problem is when you measure something, you might not measure the right thing. And we have to distinguish two types of times. We have wall clock versus CPU time. So wall clock time and CPU times. The wall clock is the time at the wall that's actually the time that expires, which is not necessarily the CPU time. So typically the wall clock time is longer than the CPU time. Unless you have a multi-core machine and you use multi-cores, then there might be more CPU time because CPU time is per CPU core typically. Yeah, so that's something interesting. But what do we measure? And unfortunately, that can be a bit different depending on your operating system. And we load this file, load clock check. So this is this file here I wrote that does some interesting testing. So we import a bunch of things from the standard library here. This is again making Python 2 compatible with Python 3, and this also. And now I have 3 different ways of measuring it. It's not very accurate, but see what I'm doing inside here. I get 3 start time stamps. I use OS times. This gives you a tuple, and the first entry is a timestamp. Then I use time clock, and I use time at default timer. This works in Python 2. Python 3, there are some changes. Python 3 has time, the time module.perf counter. It's a bit different, but if you use the time it, then you don't see a difference between 2 and 3. So I do something, I do 1,000,000 times 1 plus 1, and I say sleep for the duration which defaults to 1. So this one uses CPU, this one doesn't use CPU because it tells the operating system wake me up after 1 second. And then I do the same thing, and so that's not totally accurate because I measured this also here, but compared to this one, it doesn't matter too much. And I measured this, the second, I do the same procedure here, and I just get a second timestamp and measure the difference. So I measure 3 differences between timestamps, and then I print them out. And if I do this, I get a warning which I haven't seen before. So that's something will be removed in Python 3. Yeah. So time it. Time clock. Yeah, so time clock. And now we get a warning. I didn't have this warning before. I remember. Must be in the newer Python 3.7 version I get this warning. So that time clock will be removed, which is a good thing because it can be confusing. That's my point, actually. And you see, now you get, here on my Mac, I get OS timer and time clock being essentially the same. This is pretty coarse, pretty off. It should be pretty much the same, but they're essentially the same. And here, when I use default timer, I measure my second of waiting. So this is the CPU time. So the CPU time is approximately 0.03 seconds, where the war clock time is 1 second plus the CPU time, more or less. Yeah. Anybody is on Windows? So if you're Windows, you should see something different. Yeah, you see the different. Then time clock, it's a different thing. Yeah, because time clock here gives me the CPU time, while in Windows it gives you a timestamp since the start of the process. So if we don't look at the timestamp, the absolute value of the timestamp, when you do the difference, then you don't see this. So in Windows you have something different. And that can be tricky. So if you have a nice script that works and you give it to your colleague and has a different operating system, all of a sudden the readings are very different. That's why the recommendations use time at default timer, which abstracts this away. Yeah.
So what's again the difference between the OS time and the time clock, and in which case will they significantly diverge?
Yeah, you see, I do two things. This one consumes CPU. This is about 0.03 seconds, million times. This one doesn't consume CPU, but it waits. It waits for a second, and that's a different. So one of this timing is, in my case, is 1 second longer than the others. So the first two are pretty much the same. And the last one is a second longer because the last one also measures the war. So this one is the war clock time, and these two are CPU time. If you have Windows, this one will be CPU time, and this two will be, there will be a one there also.
And even in for the first two ones, again, in say multi-threaded applications, would they also give the same thing?
It depends how you measure. No. If you have, what you measure, if you have Python has a GIL, the global interpreter log, but it releases a GIL when you do input-output. Sleep is input-output because you say operating system call me back, and this means it's the input-output operation. So if you sleep in the thread, the other thread can keep going. It doesn't wait. So it depends where you measure. If you measure on the main thread or on the thread that waits. Of course, if you measure the thread that waits, you still measure this waiting second. If you measure outside, you don't measure it. It keeps going. Yeah. So it depends where you measure. This is sometimes can be tricky, and even in a simple application, it's might not be really clear what you actually measure and where you measure it. And if you have a complex program, it can be really, you have to really make sure that you measure what you think you measure. And typical solution is doing the two or three different ways, and on all the results agreed, it's a good sign that you measure the right thing. If they disagree, you have a problem, you find the problem. That's typically how I do it. I try to, like in Excel, I do the sum this way and the sum this way, and if it's the same thing, seems like I have all the cells to sum up. It's not guaranteed, but it's a good sign that you might miss the same cell both ways. It could happen. And something like it. You have to find two different ways to measure it, kind of independent ways, that they don't make the same mistake, hopefully. Yeah, something like this. It's kind of, it's a crutch. It's not really good, but it's better than nothing. So, and this is interesting to see that there can be differences, and if you use a different function here to calculate this. And actually, I wrote a small helper. Yeah, that's not very good, but it gives you. Actually, I can load it here. Load CPU time. Yeah, this is my small function here that measures CPU time, and I just distinguish if I'm on Windows, I use this function. If I'm not on Windows, I use something else. So this works in Linux, it works in Mac. I have no idea if it's a different operating system, but the case is there. Yeah.
Let's say I want to get rid of the deprecation warning. What is the proper replacement function?
Don't use clock.
Right, but the warning say there are two different options.
Yeah. You can actually here you can use. There's still a deprecation warning here. There's still deprecation warning. I can use perf counter. Perf counter, that's a new function in process time or perf counter. So perf counter is war clock time, and process time is process time. So let's check. So always don't guess. Check it. Time perf counter, which is new stuff now. There's also a nanosecond version. It's the final version in Python 3. So, and putting a question mark tells you, yeah, performance count for float. That's not very talkative, isn't it? Yeah. And the other one was what was the other one? Process time. And this must be the actually CPU time. Yeah, this is CPU time, the other one is wall clock time. Now you have it, and now they do this abstraction away. So if you're in Python 3.7, you don't need this thing anymore. But if you have an older version of Python, then you have to be careful. So things improved over time. So Python 3 is clearly better, as always. Yeah, and they get away. But you have to make sure to do some experiments, and some simple experiments. So take something you know what the result is and measure it, and see if this agrees what you're measuring. And of course, this approach you can apply to other problems. You know what it is. Of course, you have some different tools. Use your tools, measure, and if your tools agree with some, like if you have Linux and you have some operating system tools to measure something, use your tools and try to reproduce the results. And if they don't agree, you have to find the reason why it is. Yeah, that's important. And you also have to be a bit skeptical. If you measure something, and especially if it's a strange result, say, can this be true? Where's the problem? Maybe I'm the problem in my measuring, messing everything up for some reason, which is not that obvious. Yeah, good. So this is what I did here, and now actually you can supply this function. This is my CPU function I did here, or one of these functions. Now, if you are in Python 3, you can use these functions, and you can do the profiling here and supply this this function. Yeah, so I can do the same thing with prun, by the way. I can say prun, and if you look at it, prun also takes, if I'm not mistaken, key. Doesn't it take it? Should be an option to take a different function to measure it. Maybe I just overlooked it. No, it's not here. I thought, because with Python, with a Python profile run, you can supply actually runtime functions. So if you want to measure so you can say C profile dot profile. You make an instance, and then I specify the function. I say my CPU time here, or time it process time should be the same. We can try this in a minute, and then. Yeah. Then you get this result, and you say print starts, I guess, if I remember right. Then you see get a. No, it doesn't print starts. Didn't we say print starts? Forgotten already. Did it so many times. I have to, run. Yeah, print starts.
You have it in your loaded file.
No, I still get this one. This one works. Because this returns an instance. Great.
You gotta run return.
Yeah, I haven't executed cell, did I? I loaded the cell and didn't execute the cell, so. No, that's CPU time. Didn't I run it? No, I gave it. It must be there.
That profile
At least one time
doesn't have
you
any run attached to it.
At least one time in the code you had to do a load, an import as opposed to loading it.
Yeah. No, that should be the same because the function is there.
You gotta do s.run or something, right?
Yeah. Thank you. Run call. Yeah. Run call with underscore.
Well, no, you don't want to run that one, right?
run. So I now messed it up because I want to do it everything in one line. Profiler, run call without.
The profile needs to be an instance.
Yeah, that's, yeah. Good call. Okay. Sometimes when you're too close to the problem, even the simple things. So, so I make an instance and say run call, and it works, and it complains about this as a warning and gives me back the time. Make an instance. Yeah, and after this I say profiler. So I have to make an instance, and then no, that's a P. So I make an instance and I call it instance. Why is it difficult? Good. And I get the same thing back, and I have to supply my function as, because I can change the function. I don't want to measure the wall clock, I want to measure this one, and I made it. And I have to give this one here. That's the whole thing. No?
CPU time should be run call, and then you call the method print stats of P.
Yeah. So okay, now this works, and now I can say P run call.
Run call of CPU time.
But he's not trying to profile CPU time.
Ah,
He's trying to use CPU time as the method that actually.
yeah, I have to feed TPU time there, and then once I do this, now it works, and now I have my P, and I go step by step. That's easier. And now I can say run call, and now feed the function. Yeah, and then I get my warning because I use this function, and now I can say print stats. So it's always better to do it in one. So now you have this, and you see now the timing. Now I measure the CPU time, and actually I can say even slow. Yeah, this will take a while, but if I do the printing, it shouldn't take text. You have to wait 10 seconds for the measurement because this is still the time it takes, but the 10 seconds shouldn't show up there, and they don't show up. Yeah, there used to be 10 seconds here. There's no 10 seconds anymore because now the measurement doesn't take this into account. Okay, so once you figure this out, so doing exactly the same steps we did before, one step after the other, you get the warning because I do this. If I, instead of using this one, I use time, the time module, and I use the process time in Python 3. So in Python 2 you won't have this. Then you should get the same results. So again, after wait 10 seconds, and now you should see the process time. So you can feed a different time measurement. Per default, it takes a wall clock time, but you can also have process time. You see, no 10 seconds here. No 10 seconds here. Yeah. So in this case, it doesn't really matter what the absolute numbers are. You have this 10 seconds. Good. This is a very simple function. Let's do a bit more complicated function. I always have my Py function, and I have to go to a different directory. So we go up one directory, and then we see there's pi. So this is a very stupid way to calculate pi. So it doesn't really matter what the numerics do. So I can just import this, load this file. And this is a simple way to calculate pi. It's using a Monte Carlo approach. It's just a little bit numerics, so we don't have to go in there. And once you run it, you get actually here a value that's kind of close to pi. It's not even there, yeah? 3.14159 or something like this should be the value, and we are pretty off here. But this is a very simple numerical calculation. And the nice thing is, once we do this, because we calculate random numbers, you can parallelize it. I use it as a simple example for a lot of those things making faster. So that goes way beyond using all kind of ways to make it faster, to get it going. Yeah, and for this one you can also use NumPy. So we have, this is a version, the simple version, and then we have a NumPy version, which is doing exactly the same thing, but if you use NumPy, anybody who knows NumPy, they use random, which doesn't give you one value, but gives you a whole array of values. And this will be much faster. Has one disadvantage, it calculates all the values in memory at once, so you have to keep all the memory, where the other one has one number at a time, so it might be very slow, but it's not memory bound. NumPy will get memory bound sooner or later, because in this way I do it, it calculates all the values. It wouldn't be necessary, you can do it stepwise, but the way I implement it there. But it gives you also yeah, I haven't installed NumPy. That's not good. Forgotten to specify. So you need to install NumPy. See if this works. You should be able to do this right here. So kernel interrupt. You have to say install yes, otherwise it asks me to do it, and then there's no way to enter it. Yeah. So if you do it from the command line, it asks you. By the way, if you're here, you can open a new console terminal right in here, and you would get a terminal, and then you can do it. I would need to activate my environment here, because there's not activate. You can install it from there. This is a bit tricky here, because now it would block, but if you say yes, then it doesn't ask for confirmation. Otherwise, it asks for confirmation, but I cannot type in the confirmation, which is not that good. Yeah, so you can install NumPy and see if it works out. But it doesn't really matter too much. Here you will see NumPy as the same algorithm, and you can work with it. Good. Let's wait if this works here. And the next one actually would be Snake Whiz. So now we want to do some visualization and want to visualize things. And actually, this would be now a good way. You can do this on the console. And maybe I do the installation on the console. I make a new console here and activate my environment. And I can do my conda install here, and I don't have to do this. Yeah, so I can activate it here and say conda install NumPy. I see maybe it's not a good idea to do it twice, because here it's still interrupt. Yeah, it's interrupting. So you can install here if it works. And now we can also make a new tab. I activate my environment again. And now we want to look at Snake Whiz. So Snake Whiz is a tool that allows you to visualize the results of the run. So far we only saw numbers. It was kind of okay. But if you have hundreds and hundreds of lines of numbers, it's really difficult to see something. And Snake Whiz takes these numbers and puts it in nice pictures, and you don't have to do it yourself. And there are different ways of doing it. So you can do it from the command line. So there are different ways of doing it. So you can run Python -m. Anybody knows a -m? Actually, this is recommended if you say pip install. You shouldn't use pip, you say Python -m pip. Then it runs pip as a command line tool, but it uses the library version. Because if you say pip, it takes the one that is in the past. It might take a different pip, depends how you set up your system. Yeah. If you -m, it will take the pip that belongs to the Python, because it runs a module like a standalone program. Yeah, that's what I'm doing here. And I say, okay, run C profile. Of course, you run it from the command line, actually. run C profile, write the result to the file py.stats, which is this binary file, and run our simple program. And now I'm not in the directory. Yeah, I'm not sure where I am. And the directory. So now I do the same thing. So Python run as module C profile again with a spelling. Profile with a spelling. Write the output to py.stats and run the file simple py. So and Python missing an n, and then it should run this one and produces this output file. Yeah, it does a print on the way. And now I can use snakewiz from the command line, and I can say snakewiz, if it's installed, that should work, snakewiz py.starts, and then it opens the result of snakewiz right here, and why doesn't show anything? There should be a nice picture, always used to be a picture. Takes a while. Okay, now this is icicle. Typically sunburst is one. This is now the result of this one, and there's a lot of stuff here which we don't want. And this, you see, you will recognize this table. There's quite a things going on. This is a table of the calls here. Yeah, so this is the same thing we saw. The nice thing is here you can actually sort it. You click on it and sorts it by whatever you want. Otherwise, it's the same result, but not just plain text. And then you have a picture here. And this picture is interesting because these are the calls. And if you go in here, it shows you the function. You might not see it, but and there it shows you the function. And this is the main function from inside that takes 100% of the time. And then you go outside this function called this function that spends most of the time in this function and a little bit in this. And then the next and the next and the next. And the outermost actually, this here is a random function. So it's how much time you spend in a random function. And then this is how much time you spend in the function PyPlane in general. So this is the time you spend in the whole function. That's like the time that's in the main loop in the function. These are the other function. This is a function, the built-in square root. I'm using the square. This is square root, and this is a random function, and this is the time that you spend in the loop itself. So that's this one. Yeah. So this is this part. So we have the random function, rand, and no, sorry, here, random function, and we have the square root function, and the rest is a loop, and this calculation here. This gives you some results here. And if you don't like this, you can change sunburst to icicle, which is the same information, but instead of a circle, you have a square. Now, the inner circle, this is the inner circle, the next circle, the next circle. It's the same thing, just here. And then it's easier because now you can read the names. There's more space to put the names. But there's a lot of stuff here, a lot of small helper functions you're not really interested in. But it's very obvious which function takes the most time in this case, where the time goes, and where you might be able to make it faster, if you're able to do it. So that's something you can do from here. But of course, since you're in a Jupyter Notebook, we can do the same thing in Jupyter Notebook, and we have to load an extension, snakewiz, and you can do the same thing from here just by calling snakewiz and say plain what's the function name? PyPlane. Didn't I execute it? I executed, didn't I? So the call tips don't work, PyPlane, and I have to give it a value, 1 million. Something like this. And I used a double instead of a single, and now it does the same thing out of it opens a new tab and shows me the result, and I don't have to go to the console. Yeah, so you can do it directly from here just by using this snakewiz command. You have to load it first, an extension, so you can extend the notebook. There are many extensions. The extension has been installed automatically when you installed snakewiz. Yeah, so you get, and this is really useful because now you have this information here. And you see, now all these extra startup functions, all these little noisy things are gone because they're not measured here. Yeah, good. Okay, this is SnakeWiz, and SnakeWiz allows you to measure a few things. That's the profiling. So far, all the profiling is restricted to functions. So the most fine-grained level you can see anything is on the function level. Sometimes that's not good enough. If you want to go finer and you want to do line profiling, then you need to install the line profiler and you can go line by line. This is interesting. The problem is with line profiler, it adds a lot of overhead. So you cannot line profile your whole program typically because it would take ages to run. So typically you do profiling first, and if you find one or two interesting functions you want to go into deeper, they can use line profile on these functions, and you can do this. So again, line profiler you need to install, and then you can run it, and you have two options. So you can run it from the command line, or you can run it from the notebook, as always. So this because the notebook has an extension. So let's do both. Both of these methods can be useful. And now finally, I found Numpy to install. So let Numpy install, and I can kill this one here.
Question?
Yeah.
Is there a reason why the SnakeWiz looks differently in PyCon and in like the Untitled Console? The Untitled Console seems more accurate and has more data.
Yeah, because there are small things going on. All the startup process. The Jupyter Notebook is running already. When you start a new Python process, a lot of startup functions. All the startup functions are measured also. Everything. In the notebook, everything is loaded already, and when you do from the command line, you have a lot of noise there that happens, which I'm actually not really interested because you have to start the process anyway.
And can you do it from command line just for one function, or do you have to like measure the whole file?
Because we did this C profile on the whole program, if you generate the C stat file in a different way, then SnakeWiz will show the same result. Just the way how you generate, since we use this -m function and run the whole program, if you just use your C profile from within, everything's loaded, and you shouldn't do this one. You can try, then all these little noisy things should go away. Yeah, but good question. So why is this noise there? Okay, line profiler, you need to install it, and once you have installed it, then check where we are. We are now in the Pi measurement, and let's go up to measuring, yeah. And now I can use kernprof, which is a name. This is by Robert Kern. That's called kernprof, and you can say for both. And if you use kernprof on profile me, then you won't see anything special. This is just using normal profiling, and you just see the normal results here. After a while, you need to fortify this program. Now this is just a normal output. Again, now you see all this noise because it runs a whole module, and you have all this startup crap in here, so to speak. If I look at this, if I load now profile me line profiler. So I put a decorator here out of the blue. I didn't import. If you look at there's not import. If I run it from here, I would say there's no such thing as profile because kernprof is ejecting this decorator in the namespace. I don't know if it's a good thing, but that's what it's doing. You have to actually explicitly mark the functions you want to line profile with profile. This is deliberate. So you typically don't want to line profile all your functions. You don't want to line profile hundreds of functions because it takes very long. So you have to explicitly say, I want to use these ones, these two. And now, once I go to my, line profiler, and I profile this one, and I also have to give the option that is supposed to do this when I say -L for line. So I turn on line profiling, otherwise I wouldn't do it actually. And then now it takes longer. And after a while, it will show you everything line by line. So it takes a while, but once it's working, we can look at the version that actually works in. See, now you have this line by line. When you see here, if it's fast, you can still something by 0.6%. This is a time percent, and this is the total time here with units there. How much time it spends here and how much time it spends here. And here in slow, you see this would be 0% because this is so slow that there's nothing left. I mean, if you round it to 1 digit in percent, you don't see anything. So this is a very simple. It's a very simple function, and you have this very simple result. So let's do some small examples that make a bit more sense with line profiling. The next one would be actually accumulate, where I wrote this very simple function that hopefully makes a point about this line profiling. Accumulate, you see, now I do this. This does nothing else but adding up numbers in a list and keeps all intermediate result. Yeah. So if you use Numpy, then you might know accumulate.
Does this profile decorator, can we import it from a package so that it actually...
Yes, you can do. I will show you. Typically, I do it from the notebook because this is something you do only once, and then you don't have to put the decorator there. Yeah.
What were the 2 functions that you loaded right now?
Hmm?
What were the 2 functions that you just loaded right now?
Accumulate.
Accumulate. What was the one above it?
Yeah.
And the one
This is use line profiler. So profiler, use line profiler. Everything the directory measuring. You see, this one just it calculates. If you do this, you see, I say accumulate. Yeah, I cannot run it. I cannot run it because it's decorated. I need a decorator. Take a decorator out. When I take a decorator out, then it accumulates it. And if you, because I don't have it printed, and the result accumulate, you see, adding numbers from 0 to 9 gives you 45, and this keeps all intermediate results. Okay, so I did this one. Now we can do line profiling here and run it for 10 and 100. So we do the same thing. But instead of using profile, you use accumulate, and then it works a while on it, and then you see the difference between these function calls. When you see, if you run it here, this is the time is pretty even distributed between these 4 steps. This one doesn't take a lot, and this one not, of course, but they take about more or less 25% or so around it. Yeah. So that's something you know. There's no one line that consumes all the time. Yeah. But you can see something. You have this breakdown line by line. Good. A few more examples for line by line. So you can always do some experiments, load some calculations, some different types of calculations. So I do here a loop, and I add 10 to a number. I multiply a number by 10. I use to the power of 10. Then I use the power function, which is doing the same thing. I use a square root, mastered square root, and I also set square root to mastered square root, which saves me a lookup. And do this again, and I just access square root, and so on. So it's a few things here, and then I run it through my line calculator again and see the differences. So I will show you the code also. And then you see what takes how much time. And you see here, then when you have plus and multiplication takes about the same amount of time, very similar. Power is more expensive, and the power function takes a little tiny bit more time than this double star here. And you see square root, mastered square root, and square root, there's a difference here now. This is always relative to the total time. You have to be careful, yeah? So if something else takes a lot of time, everything gets to 0. But you can also see the absolute time. So there's a small difference doing it this way and this way, if you repeat it so many times, yeah? But you see if you access mastered square root and just square root as it is, there's a difference because there's an extra lookup. So that's something you can investigate here, and you can work with it. Good. So 3 o'clock is break. It's 5 minutes to 3, so maybe it's a good thing if you make break now. Then you have a better chance to get a coffee. So we have 20 minutes break, I think. So then we meet back here 15 past the hour, which is 20 minutes. So we move the break of 15 minutes, and we continue with some more of these little bit profiling, memory profiling in algorithms. So we meet here 15 past the hour and continue with our tutorial.
something you were saying early on about sort of using a better algorithm versus like approaching the problem with optimizations or language changes or something.
Yeah.
There's an exercise in a very commonly encouraged book for people to look at called Think PyCon, I guess.
Yeah.
One of the exercises is kind of like in this chapter where you do wordplay related stuff. If you kind of solve it in more naive ways that they suggest, it takes close to an hour to run. If you use recursion and sets and a few other features that are not maybe introduced at that point, you can get it down to like a couple seconds.
Yeah, that's algorithm. That's a big, can make a big job. If you have a problem that's super fun, people solve it right. If you can use Python data structure that's super good, you get the algorithm really to be good.
So it's a combination of both better,
Yeah.
better features.
Question for the buffer declarator. Do you make, do I have to import it in a file or do you use something
It
special?
only works when you use cone prof. Do you see it? You can use from the notebook. I show you the next thing. So you use a notebook decorator, then you have to use the structure.
And when you use current proof, would you have example like smaller?
That's a conprof. As a conprof.
And this means use the line code file, the rows, give a lot of output in the file. This one has to have the functions you want to measure decorated.
And then the profile declarator will work.
It will check the decorator in the namespace automatically. And then
Okay, can we continue? Good, so now after the break, let's continue. So we are building our line profiling thing. So the line profiler is a bit tricky. So you can use a decorator, and you don't import the decorator. Then this program only works with the current command line tool. That's one way of doing it. The other way would be actually running it using the notebook, running the notebook. I just jump ahead and do in the notebook. So if you do this, you have to load the extension line profiler. So very similar pattern as before. So I make it bigger here. So we load the extension, line underscore profiler. Yeah. And now we have this, it's already loaded. It doesn't matter. It's there. And now I can, for me, because I think I put it in my config file to load it anyway, or something. Now I can use lp run. We have a new command called lp run. And this lp run, now I can say I want to decorate this function. And that decorate the function is an option. I say use fast, for instance. Use fast. I want to decorate this function. And then I want to run this. And I want to have the function fast. I want to have both of them, and then I say use fast. And I run this one. Yeah, so I have this. This is equivalent to putting the profile decorator on these functions for the command line. So I have to still do it, but I don't have to change the source code. It's equivalent to putting the decorator and running on the command line. You see now I have these both functions, and this is the same thing as I did before. So I can run it here and can work with it. So that makes it a bit easier. So lp run uses the same source code. Actually, just the interface is different, and you don't have to put decorators in your code. Good. So I have a bunch of more examples. Next one would be local and reference, local ref. So I did this some very small examples here. So here I'd actually do it. I try to use a decorator, and if it's not there, actually I throw a name error. Otherwise, if the decorator is there, so now I would just have my own function that doesn't do anything. I just create my own profile. Now I can run it from here, and why does it? That's strange.
Excuse me?
Yeah.
Can you explain again the syntax of your line with LP run?
Yeah. So
use fast, and again you use that again fast and use fast.
yeah. So I want to run this function. This is a function I run, and this function I decorate. This is equivalent. This is equivalent to this source code up here. So this minus f decorates this function. Decorates. Actually, this would be equivalent to decorating this function and decorating this function. Yeah, so the minus f decorates this function, so to speak, with a profile decorator, and then I run the function itself. So you can play around with it a little bit. So I'm not sure why this not worked. Well, probably I executed the cell before. I did something strange. So here now I have these two f's. If I don't decorate this one, then now see I get two functions now measured. If I only decorate one, this will only measure one. You see I get only one now because I decorate only one. So you need to decorate them, so to speak, with this -f option and mark them for line profiling. Again, when you do line profiling, typically you just want to profile a few functions because it makes your code potentially slow, factor 100 or something like this. Here you don't see it because it's so fast, it's still immediate. But if something takes a second, it will take 100 seconds or longer, that might be very painful, and you have to wait so long. Yeah, that's why you have to explicitly mark all the functions you want to profile. So again, first you use normal C profile and profile the whole program. Use SnakeWiz and look at it and find, that's the function I want to look at. And then you can go to this function and do line profiling in the function. That's a typical process. Or if you find 2 or 3 functions, then the line provide 2 or 3 functions. If you have 100 functions that are equally slow, it gets difficult anyway to do anything about your program. Then you might rethink. So you might not resolve the problem. If you have 100 functions and 1 or 2 is slow, then you have a chance to go to this function and make it faster, potentially. Good. So this is something you can do here with this line profiler, and you can measure a few things. And here I have a profile, different functions. Here, local ref and so on. Let's do this from the command line again, because I decorated them here. So I can use my cron prof, yeah, and I say local ref. It takes a bit, and then it is profiling these functions. And then you see it, if there's a difference, if you do different kind of names, using different kinds of names in the local namespace, the global namespace, and so on. See how long it takes. Typically, it just take a fraction of a second to run it. And now you have to wait so long. Yeah, and now you can compare these runtimes. Yeah. So if I do this, if I set the square root as a local variable, then it takes about so long to access it. If I say mass, it takes a bit longer. So in terms of percentage, it doesn't change a lot. Yeah. So here it goes up from about 49% to about 53 if you run around it. Yeah. So it's a bit different, but not a gigantic difference. So it always depends what else happens in your program. Yeah. So this makes it a bit faster because now I only need to look up a local name. Here I always have to say I have to find the mass module name first in the global namespace and then do another attribute lookup. There's 2 more lookups in namespaces. Yeah? This one finds the local name. This one looks for mass. Can find it as good as a global namespace, and then once you find the module, you have to do another lookup. So it's 2 more dictionary lookups, but dictionary lookups are very fast. Because I use so much. So that's what happens here. The same thing now, if you measure them, you have some differences in this module lookups. There's a little bit of difference, but not much. Not much. Yeah, those kind of things. Good. So you can play around with it. Let's continue with our topics. So this is CPU measurements. I think the exercise, because we don't have much time, you have to do it as homework on page 32. And I keep going with memory profiling, and that's maybe a good idea to make a new notebook. And I call this memory, and then the other name wouldn't be fast one, doesn't make a lot of sense. I call this CPU. Yeah, so makes more sense. Okay, the next thing would be memory profiling, and this is a totally different topic. So very often when you talk about making things faster, you talk about CPU. Yeah. This one?
No, for the profiling of the local ref and multi-ref.
Yeah.
It's surprising to me. I don't know if you have the same result. That the function task takes like 20 seconds, but the 2 functions which it calls together, they take like 11 seconds. Where does the 9-second difference come from?
That's a good question. Did it introduce some overhead? I'm not sure how those times add up, because this is about, it's about 11, and there's 9 seconds somewhere.
Is it CPU time, so it overlaps 2 CPUs?
I'm not sure. I cannot answer. I'm not sure where this comes from. Maybe this because this line profiler adds quite a bit of overhead. That's the overhead of line profiler itself. Maybe. So I'm not sure. I have to investigate. Yeah. There's some things are not totally clear why this is the case. Yeah. So I have to think through. I don't have an immediate answer for this. Okay. Sorry. Let's continue. Memory measurements. it's a totally different story, but sometimes memory can be a problem. Nowadays, computers have gigabytes and gigabytes of memory. I still remember computers only have megabytes of memory, and they still work somehow. Now we have a lot of gigabytes, and if you have a big machine, you even have terabytes of memory. But you can still use it up easily if you want to. There's no problem. So let's do some memory measurements. You can do this with Python things. You can say sys get size of. And you can measure the size of something. Who knows how big are integers in Python? In Python 3? 28. Yes, 28 bytes. If you do it in Python 2, it's only 24. Because in Python 3, longs essentially became int. Yeah? If I do the same with a bit bigger number, yeah, so if I hit something bigger than 64-bit integer, then this gets also bigger. Yeah, so because there's a Python int, internally it's stored as an array of integers actually. Yeah, that's why you use more memory. So if you make the number bigger, then you get it bigger. Yeah, so if you don't want to type so much, you can also say. Yeah, so you see now it's getting even bigger. Then you have a bigger number there. Good. So if you make a list, let's make a list. Make a big list, let's say our million again, so I can do this here. Yeah, and I measure the size of a list. Actually, what do I measure? If I say sys get size of my list, this measures the size of the list itself. Because if you multiply, I'm too lazy now, here, this times 28, then you see this wouldn't work. So the million numbers take more memory than the list, because this size of measures only the list itself, which is just a reference to it. 8 bytes. That's pretty much 8 bytes. Yeah, a million times 8 bytes, and a byte is 1024. That's why, if you do this, you get this number. So something like this. Yeah. So this is if you use get size of, you only measure the object directly, not what's contained in the object. So you would need to do it yourself to get this measured here at this place if you want to do something like this. If you don't want to do this, then you can use a tool, and this tool I'm using here is called PyMpler. I think that's how it's pronounced. This is a tool that grew out three, no A, pronounced with A, but no A. Yeah. There's 3 tools. They're called A size of, heap monitor, and Muppy or Mappi, whatever it's called here, and they are joined together for quite a while, and they form this project. And this makes your life a bit easier because you don't have to do all this manual measurement. You can do a few things here, and one of the features it provides is the tracker. The tracker, and this allows you to do tracking of memory. That takes a while, but I can say my memory tracker. So I'm lazy here, called just M memory tracker. Is module tracker class summary tracker. So different trackers, I use a summary tracker. When I do this, you see it will take a while. This will take a while, and now I have this summary tracker here, and then I can say memory tracker print diff, and it prints the difference to before. This should be supposed to be about 0, because it always shows the difference in the last measurements. And we didn't have last measurements should be 0, but you see it's not exactly 0. So rule number 1, when you measure memory, there's always some small mistake, there's some small problem. We are looking at megabytes, we're looking at bytes here. So if you have a memory problem, typically you consume a lot of memory, and then you want to see where your megabytes or gigabytes go. And this is supposed to be 0, as you see here, more or less. Not 0 yet. If you do this again, then actually you will 0 in, and then you get 0. It takes a bit. And you get a list of everything that's defined right now. Yeah. See, now it's pretty much 0. If you call it again, this is pretty much 0. It's just still a few kilobytes here, and you have the number of. And here you have negative objects, and it doesn't exist. You cannot have a negative object. Antimatter or something that's not in here. Yeah. So this is a mistake. So you have to be. You should take it for it works for big numbers, but doesn't work for small numbers. It's important. Otherwise, you might chase something that's not there. So now I wrote a small tool that uses this one and measures your memory. And actually, I use a decorator. Who knows how to write a decorator? Just quite a few people. So decorator is a great tool for these kind of things. And I go to the measuring directory, and here we have this a memory, different types of memory, and I use load memory size p by employ. So this is the file I'm loading. Loading here again. I have my Python 2 compatibility stuff up here. I import my tracker, we just imported, and I use a global dictionary. There are many different ways of doing it. You don't have to use a global dictionary. There are more elegant ways of doing it, but it's very simple and it's good enough for our purposes here. And I write a decorator. So a decorator is a function that takes a function and returns a new function, typically. And you can use the add thing to use it. Using a decorator is still simple. Just put it there and that's it. Writing is a bit more involved. Typically, you use nested functions, as I did here. And use functool wraps to make this function nice. So this is a function that will be decorated, and I need to wrap it. And this is a function that replaces the original function. And this is actually the code. You see, I make an instance of my summary tracker. I call diff twice to get to 0. If you want to be paranoid, you can call it 5 times to get really get 0. The more often you call it, the closer you get to 0. But it makes it much slower because you have to wait. And then I call the function here, and it's important that I have the result here first, and then I return the function I use finally. So when you do a try finally, the return is not active until the finally is executed. So I do the my memory measurement before I return this thing. That's what I do here. So I use a try finally here to make it. Yeah. So you can try it. The finally will be executed before the return finishes the function, so the result still exists inside the function. Yeah? And I'm just use my measure my diff here, and I store it in the dictionary. You see, this is this dictionary, this empty one, and I use the name of a function as a key. So if my function is a name, I use every function has a dunder name here, and this is a string, and I use it. Yeah. So and then using it easy, you just put it here and say, okay, make big, and I just create a list of a certain size and return it. And when I do this, now I should have done it earlier. It takes a while because I'm now zeroing this twice and then do another measurement. I call the summer tracker 3 times, and every time takes like 10 seconds or so to get there. So it makes your program much slower. There's nothing you can keep in production. It's only for your test environment because it slows down. This function takes nearly no time, and now it takes so long to run, and it's still running here. You see, as long as now it's finished. You see, now I get this measurement. And now you can have this measurement. You see it uses the name of the function, make big, as a key. And then you get a list of these objects that are new, that haven't existed before, because I zero it out, and then I do the measurement. And you see, I get int. Shouldn't it be 1,000,000? Why is it not 1,000,000? Anybody knows why we don't have 1,000,000 numbers here? Yeah, there's some we talked about it. So when we in Python, and I have a number a, and you can say sys get ref count. Then you see this one exists only once, and it will be referenced in my case 10,000 times. Actually, the most referenced number is which one? 0. Yeah, 0 will be nearly twice. Yeah, 5,000. Oh. Why the one has so many? Typically the 0 has more. That's strange. The first time obviously 0 was a winner. Now the 1. Maybe we created a lot of 1s. If you restart the kernel, probably 0 will win. Yeah, but this is the object exists only once, and you have so many thousand references. And reference has only 8 bytes, and an integer object has 28. So you save memory, and typically reference also faster. Python. You can solve every problem with another level of indirection, and reference is a level indirection. But in Python is a good thing. That's why it's not a million here. If you start everything from scratch, there still will be a few, because and if you calculate the numbers -5 to 256 in C Python, this is the implementation detail that might change. If you use a different Python implementation, these numbers are different. I know Iron Python has the numbers -1000 to +1000. I have no idea what PyPy is using or some other implementation, JSON or something. Yeah, so this is the implementation detail to make it faster. And you see, this is the size of the list. So the list itself, and then the numbers in there, you get it broken down by data types. Yeah, so this can be helpful, but makes your program very, very, very slow. Yeah.
You were saying before that when we were calculating the size of a list, we just got the size of all the references. This is doing it still that way?
Yeah, because this one is doing it by data type. So it gives you the list itself and the integers itself. There are other functions that merge this together, and you get the list including everything contained in the list. A size of is just what's counted in there. So this is my first decorator. So decorators are very useful for these things. Yeah.
So since the list is 9 million bytes, if I
Yeah.
read it correctly, does it mean like one pointer is roughly 9 bytes? Like this is like the Google pointers essentially, right?
Yes.
So like the size of each one is roughly 9 bytes. You can infer from this.
So there's the container itself plus this million bytes, million references. So the list itself also needs some space. And you have to be careful. We come to this. When you have a Python list, it's not exactly the size. Python, with this one, we will see Python will allocate more space than actually in the list. I will have an example for this. We will see this. Then we come back. So in 10 minutes, we come back to the question. So I have another one. And now it grows. I say about growing memory, load, memory. So it's a bit different. So now again, I have this time I don't use a decorator. I use a different approach. I use an explicit function that takes a function and the arguments for the function. Very similar, but I don't use a decorator. A decorator you have to put in the code here. I don't have to put anything in my code. I just use a function. So a different technique to get a very similar result. Again, we make an instance of our summary checker, zero it twice, and then we call the function, and now we return the diff. Yeah? And then I do this again, and I have this function that just returns the list. And then we have this function which is different. I have a global data, and then this function grow, it's manipulating this and appends to this. Yeah? And of course you see it, data will grow and that data will exist. If you return something, and I call this function as here, but I don't store the result, I just print it, it will go away. It will be garbage collected immediately in Python. Where here, I change some global, let's run it, it takes a while. Yeah? So here I return something, and this one shouldn't consume any extra memory unless I save the result, but I don't. I just call the function, and I print the result of the memory attacker, but I don't store the result. Here it's different. I have a global data list when I append to the list. Here it's very obvious. This is a made-up case where I know the result to see if my measuring corresponds to what I'm expecting. In reality, you might not see if anybody is changing some global structure somewhere. You should not do it, but people still do it. So typically, you want to write what's called pure functions. If it's possible, the function doesn't change the outside world. That's typically the easiest to reason about it. But sometimes, in terms of performance, it might not work, or for some other reasons. And now I can measure this, and you see, this one doesn't consume any extra memory. There's no difference before the call, and this one giving me this result. And now my list has a little bit different size. It's not exactly 8, 9 here anymore. Yeah? But this one now consumes memory because the data empty list stays around after the function is called. So again, we make a simple case where we know the result we want to produce and see if our measurement reproduces this one. and its reasons about it. Good. That's one thing. So now let's have this one to see how a list grows in memory.
So what does it mean that there's 0 objects in the list?
There's no changes. There's a change before and after. So after the function call, there's no extra memory consumed. Here, the second one consumes memory because now data is much bigger. This data has a length of 0, and after this, the data has a length of 1 million.
I mean, in the list.
Yeah, so there's no new element.
So it's
So it's the same list because it's listed, but now it has been...
Because the list already exists. The list data already exists. There's no new list. The list itself there's 0 increment in terms of number of lists, but the size of the list grew. Yeah. Yeah.
The first example, the list got created, the memory got consumed, but once the stack roll, basically, it got removed. That's why they did 0.
You mean this example up here?
No, the one you, like the make big example. Like the list was created, but
Yeah.
because it was returned,
Yeah.
I guess the stack
Yeah.
was unwind.
Yeah, and if you return it in the minute return it, but you don't create when I call this function here, that's what I'm. So this function calls a function, but it doesn't save the return value. Just call the function, throws the return value away. And in this minute I call the function. If I would say result equals, and then return the result, then the function would exist. If I keep a reference alive somehow, but there's no reference. And C Python works with reference counter. The reference counter goes to 0. The garbage collector collects my list and it's gone.
Immediately.
Yeah.
So it's like in C++, basically, right? The destructor.
Yeah. So if you use PyPy, things might be different because PyPy uses a different garbage collector, and this object might stay around for a while. Because C Python uses a reference counter, so as soon as a reference counter goes to 0, it will be cleaned. If you use a mark and sweep, then the object, like in Java, might be there for a while until it's cleaned.
And this list was on the stack or on the heap? Like where did the list reside? Do you know or not?
I don't know. Must be a mistake, I think.
So then it's basically as the stack unwinds, like we go back.
Yeah. Yeah. So if every object has a reference counter and it goes up and down. You can check. You can also say, as we get the number of references. Yeah. I think the minimum number of reference object is 2 you get because as soon as you use sysget ref count of some big number that doesn't exist. Yeah, then you get a ref count of 3, which is some artifact because sysget ref count itself creates a reference. It shouldn't be on 1, but it's 3 because it measures its own doing also. Because this number is created and thrown away immediately. Yeah, it's a bit tricky. Yeah, but the thing is, there's no reference anymore. If you use a different implementation, you might get different results. I'm not sure if PyImpl works with different Python implementations. Good. So now let's look at how actually a list grows. So I just I let it run because it takes a while. So I import a size of and flat size are 2 different functions from PyImpl, and I have a function that I call here. I provide the number, the size of a list I want to calculate, and then the function itself, and I feed a function. And I make a list, and I make a new list which gives me the current memory size of the list, and now I go through the length and make my list longer, append to my list step by step, and every time I measure the size of my list. So I get the size for every list, a list with 0 elements, with 1, with 2, with 3, with 4, and so on, and see how much memory it takes. And then I feed it 3 different functions. So I have a list of 1,000. You don't want to make it too big. And then, actually, I should use a matplotlib inline, and I have to install matplotlib. So see, I've forgotten to install matplotlib, but I can do this at the command line. Yeah, so I forgot install matplotlib to show the plot. I don't know why I didn't put it there. So then you should see the plot actually, but you still should see the output here, because if I don't have a plot, I haven't executed it yet. you still at least see the numbers. So I have this, and I feed three different functions: flat size, a size of, which are both imported, and then this get size of. So I have three functions. You can put more functions. Yeah? So functions are objects. I can iterate to a list of functions and feed these functions to my there. So this thing, this size function will be one of the three in turn. Yeah? A size, flat size, and this get size of. And then I do these calculations and return the memory. And this is just some output here. This is not important. It just makes a table and a plot. Yeah? But just to show the numbers. And when I run this, why doesn't it print it?
I think you need to call main and then
Yeah, I didn't call main, so I can call main here. Yeah, and now you get the. Yeah, so Matplotlib is not installed yet, and that's why it's still installing. If you have a plot, you would see the plot, but now you see the sizes, and you can compare the sizes of these things, and they are different. It's not so easy to see here. That's why I have to wait until Matplotlib is installed, and then I do the plot. So, and once you install Matplotlib, then you can say matplotlib inline, yeah, and then I can inline, and then I can do this again, and then you get this size. And now it's very obvious. You see how a list grows into steps. This is the size of a list, goes from 0 to 1,000 elements, and the list doesn't grow continuously, it grows discontinuously. So Python makes, there's a formula actually, Python makes it, let's say about 50%, it's not exact. As soon as you reach something, Python says, give me more memory, and makes the list bigger. So it consumes more memory than is actually necessary, and makes the list bigger and bigger and bigger, and that's why you see the steps. And that's a good thing. You need a bit more memory, but you make things much faster, because allocating memory is a pretty slow thing. So everything has to do with memory. You might be familiar with this term of starving CPU. So in the early 90s, CPU memory was more or less the same speed. So CPUs got maybe 10,000 times faster or something, very much faster. Memory only got a little bit faster. So very often you have a big CPU, but you're waiting for the data coming from main memory. Yeah, that's why you have all these caches, all these things. And this is the compromise in Python, to use more memory, but you don't need to allocate it, because allocating this memory is pretty expensive. Because you say, oh, operating system, I need more memory, give me more memory. And say, oh, okay, you need continuous memory, I have to clean some memory, doing a lot of things in the background, more or less. Yeah? And if I have quite a big chunk of memory, then it's much faster to do an append. That's why append is a pretty efficient operation in Python. But only the end. If you do insert, it's a different thing. Yeah, because you have to rearrange the whole list, which is not good. And this is nice, you can visualize it here, and you have these different ones, and this one measures only the list itself. And you see it's big jumps, yeah? Big steps. And this one measures the list plus the integers. If you put new integers, you see now the steps are much, much less pronounced, because integers take a lot of. So even though you use more memory for the list, but in terms of your whole program, it's very little. It doesn't really matter too much. So you don't waste a lot of memory relative to the whole memory usage. Yeah. So this is the first function, which is flat size. The next one is a size of, which measures everything, and then the last one is the same picture as the first one, because it's just get size of. Yeah? This is interesting, because now you can visualize if it's what it's really doing. So you want to measure something, even if you know this fact, it's pretty abstract. If you make a picture and you made it yourself, then you know that's what I measured and that's what the tool is doing. So that's the purpose here to measure something. Okay, this is memory measurement. So you can do this. Now I have a second one that's actually the same thing, but you just remember how many allocation steps you have. So it's a list allocation steps. Yeah, and now this one is running. And you see, when I do 10 appends, Python allocates 3 times. If I do 100 appends, there are 10 allocation steps, and so on. And if I go up to, this is 10 million, so if I do 10 million appends, I only have 104 allocation steps, which is nothing. Yeah. If you do 10 million allocation steps, we can talk about tomorrow when you're finished. Yeah, that takes a very long time. So you don't want to do this. Yeah. Therefore, this is just the same information, just shown in a different way. It's the same.
And if we did it like what you did before, like list, range, and stuff, would it be one allocation or more? Like if we like.
Yes, list range makes one allocation. Because Python knows the size. So a range object is nothing yet. So if I say range something, this is very often people say it's an iterator, which is technically not true. It's very similar to an iterator. If you say range, now Python knows it will be 10 elements. And then you can allocate the whole thing immediately. It doesn't have to do append. Yeah. The same thing if you say, this is also one option. Because Python knows there will be 10 A's, you can allocate immediately everything. That's the fastest way to create 10 A's. If you don't want to type 10 A's. Yeah. So range is the same thing. Range object, Python knows how big it is and know how many spaces to allocate. There's no need to do this. If it's an iterator, it doesn't, because it doesn't know. We can always say next, 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 next until it gets to iteration, so you have to grow it incrementally. It would be interesting to change list range, how long it takes versus converting range into an iterator and then converting iterator into a list, measure this one. If there's a difference. It should be the same memory at the end, but there might be a time difference, so I'm not sure. Good. Again, this is everything done on this global scale, so you see the whole memory of the whole program. There's also something called line profiler, memory profiler, which goes line by line. Unfortunately, the results, especially on my Mac, are not really good. So it works. Technically, it shows you some results, but the results don't make any sense on my machine. It's a good example for tool. If you use a different operating system, you might be more lucky because Mac compresses memory. The newer versions of Mac, as if they don't use something, Mac is compressing the memory, and then my measurements don't make any sense anymore, how much memory I actually use. Yeah?
Are there any tools that can deal with sort of, let's say you had threading and non-deterministic amounts of memory used, and looking at peak memory as opposed to like per function? Any recommendation?
I used the other tool, I took it out. You have to find out when the peak happens. You can measure memory any time in your program, but you need to figure out you have to have a notion when the peak happens. And it's very expensive to, as you can see, if you do something like this. As you do summary tracker, if you measure the whole program, all objects, is very expensive because you have to go through all the objects, visit all the objects that are on memory. If you know the object you want to measure, it's not expensive. It's much faster because you only have to measure this one object. Then you can kind of monitor this object and find out when the peak happens. If you don't know which object is big, then a program that runs a few minutes might take weeks to run, or something. I don't know, but it's not. Doesn't make any sense because you won't get any result in a. Because typically you don't want to measure on once. You want to measure different variations, and so there's no way to get somewhere. So I'm not aware of a tool. I didn't find many tools for memory measurements, so it seems not that easy. Yeah. Good. So this line profiler thing, it's here. It works exactly the same as the memory profiler works exactly the same as line profiler, and you get a result. And but it's not really useful because what you get out there, doesn't make any sense. So that's just an example of a tool that doesn't really work as I expected, at least not on my machine here, so which is not helpful. Good. We only have a few minutes left, so this is a profiling thing. So it's more about principle because those tools are very big and you can do a lot of things with it. But it doesn't make sense to show you all the options because you can remember anyway. The thing is, you should use a tool, but when you use a tool, you have to take with a grain of salt because tools make mistakes. Yeah.
I think the class goes till 4:40.
4:40.
Yeah.
Okay, then we still have some time. Great. Yeah. So we still have 45 minutes, but we still have a little thing to go through. Good. So this is a profiling part. I still want to finish up the profiling part, and now we come to some algorithmic and anti-pattern part, a few small tips. So what you actually do to make your program is very, very different depending on the program. The thing is about learning a few principles, how you could do it, what kind of options are there, and which way you might want to look. So again, the first thing is, if you change your algorithm, potentially you can gain a lot. But first you have to find out what your problem is and if there's a different algorithm here. You can use standard library modules. If they don't do it, you can install extra modules, as we did with Numpy and those kind of things. Depends on your problem, they might be very, very useful. So Numpy is not only faster, it makes your work much more convenient if you work with numerical arrays, because you can do a whole array operations and you don't have to write list comprehensions all the time and things like this. So this is something that can be useful depending on your problem. Now I want to show you a few examples what you actually can do. And since we have our CPU and memory measurement, now we're doing a new notebook. Oops, new notebook. And we call this so the first thing we need to do is have a notebook, always rename it. Otherwise you have untitled 1, 2, 3, 4, 5, 150. That's not going to help. In the long run, algorithms. So I want to show you a few algorithms here, what you can do with Python. So the first one is the old one, which is not really valid anymore too much, but used to be. But it's still recommended not to do it, because if you use a different Python implementation, you might have this effect, and this is string concatenation. Yeah, so string concatenation. So you can do something like this. String is an empty string, and then you say for I have a different example here. I thought I have a different code. Yeah, so this is the solution. So there are still two different ways of doing it. So this is my string, my beginning string, and this is my n, how many times I want to put it together. And now I can say the first way would be, if I have these things, for x in, so do it like this, for x in range n, or if you want it actually, you can use underscore here because we don't use the x, then you say s plus equals a. So this creates a string with a 1 million a's. Yeah, so that would be one way. In C Python, that's not a problem anymore. It's optimized away because it's a very common case. But typically, it's not recommended to use it. If you use a different implementation, then this might not be. I think you use PyPy. That's not going to work well. The typical way of doing this would be using join. In this case, not adding this together. Actually, the fastest way, obviously, is using a times a million. Yeah, this would be the fastest way doing it. In this case, here, yeah, that would be much faster than doing this plus equal, because this plus equal can be an anti-pattern. If you look at it, because strings are mutable, that means you have to create a new string every time. This is a special case. C Python optimized the way other implementations might not. There used to be always a big problem, but with a modern version of Python, there's no big thing anymore here. You can do it, but it's still not recommended. So if you look at a Python documentation, they tell you not to do it, but you can. String concatenation can be a problem here. It's not very big, so, but it's one of these things where an algorithm can make things better. So list comprehensions are a bit faster than loops. Not much though. So I have two ways. If I have a list, yeah, make a bigger list. So I can say my result is new list x plus 10 for x in L. Yeah. So this would create it. This would be equivalent to a loop. And if you want to write a loop, you can always take exactly the code and rearrange it, which would be equivalent to a list comprehension. You need to have a list result first. So let's call this result 1. And let's call this result 2, which is an empty list. And then we go through here. Not n, L, x. So, okay, that makes more sense. And this would be an append. Yeah. So these would be equivalent, which we can see because now we say result 1 equals result 2, and which hopefully gives us a true. And now we can measure it with our tools. This is a one-liner. Time it measures this one. And this is a whole cell. That's why I have to use a 2% time it. So we use our tools very quickly. And then you can measure. There should be some difference. It's not huge, but there is some difference. When you do it, hopefully. Yeah, so there's some difference. It's a few percent faster when you use a list comprehension. Doing exactly the same for this case. Of course, list comprehensions are restricted. You can only use expressions. You cannot do it try except or anything like this. In a loop, you can do it try except. You cannot do it. With Python 3.8, things were a bit different because the walrus operator, this new, you can assign something in an expression. In 3.8, we don't have it yet. Then increases what you can do with in the list comprehension. But right now, this is something, a small thing. It's not too much a difference here, but you can do something here. Okay, the next one is actually the local global thing. So we have all these ones, and then we have this local global. It's not in measuring, it's in algorithms. Local global, local versus global. So we had this before. So I have a global here, which you should, if you use PyLint, then ask you to make it all capital, which I did here. And I do access this global in the loop all the time. And this is a small change. So I create a local, which is just a reference here. And I access this local in a loop. Very simple code. It's the simplest as you can get. And of course, if you want to measure something, you need it repeated many times. Otherwise, you won't be able to measure something. So and if I do this, and I use my profiler here and run through my profiler. Yeah. So you see profile, make an instance, and run the stats. And you do 100 million runs here. And then you see, if I make it a bit smaller, the differences in runtime, repeat and repeat local. This is 3, and this is 3.8 seconds. There are some difference. There's some difference accessing. Because what does it mean? Here I access this local, I just at one look up in locals, and I find local, and I'm done. Here I look up this name in local, cannot find it, and I have to go to the global dictionary and find it from there. So it's one more lookup. And I do it 100 million times, that's why 100 million times, 0.8 seconds, not too bad, but it's something that happens. Yeah. But notice I don't do anything else. I only look it up 100 million times. So if you look something up a few hundred times, you won't gain much. Where should it come from? So this is a bit artificial here to do. Now I take it one step further, and instead of load built-in, local versus built-in. Yeah. So now I don't only use local and global comparison. I use a built-in. So sum is a built-in function. So built-in is everything that's not a keyword, but you don't need to import. So sum is a built-in function in Python, and I'm doing the same thing, accessing the function sum. I don't do anything. I don't call it. Otherwise, the function call would shadow all these differences. I access this function sum here Or I've created a second one, so a recommendation, you shouldn't override sum, so you use an underscore at the end. That's the typical thing if you want to use the same name. You could also use a different name, but some underscore. And now do the same game again and do my profiling and measure how long it takes to access this sum. Now it's another lookup. I look up local namespace, I cannot find it. Go to the global namespace, cannot find it. Go to the built-in namespace. Another lookup. And if I do this, then you see now I'm going from 3 seconds to 4.4 seconds. Yeah? The 3 seconds is the same as before. With the global was 3.8, now we are 4.4 seconds. That's something. But again, it's still contrived example because I do 100 million loops to get there. As if you have a few accesses, you won't gain much. But this is one thing you can take into account. Good. So those kind of things can be interesting, and you can try something, but they won't buy you too much. But what buys you typically much is using different data structures. You might heard about when people talk about data structures, if you use the right data structure, you solve your problem, which has some tools to it. So let's look at some data structures. First, we start with some built-in data structures. So data structures and can I write anymore? Structure. They belong together because in Python, when you use a data structure, it has a lot of algorithms behind the scenes. You might even see. It's like the append is the algorithm that does a lot of things. It balances your list and appends all kind of stuff. And they are typically written by people that know what they're doing, and you don't have to do it. You don't have to reinvent the wheel again and again. It's there already, and you should use it. So let's look at some data structures, which ones to use. The first one is list versus set. So list versus set. So to see, I'm missing this one. List versus set. And you can use a list or you can use a set. And I can say load searching. Oh, yeah. So this is a very common thing. So I have my time it here. So I use time it. You can also use time it here. And I have two functions. One that searches in a list, one that searches in a set. You might be familiar with it just as an example. So here I create a list of a certain size. I don't measure the creation of a list. And then I get my timestamp. I do the searching in my list, say, is n in my list? So n is the last element, this is the worst case. You can also search for something that's not there. If you want to make more realistic, you go for the middle of the list. It's very important where this n is contained in the list. N is the last element. Actually, it's not contained, it's not in there because n is larger than the list. And then I create the timestamp here. The difference between this is my current timestamp and this is my timestamp before, and return just the time. And then I do the same thing. The only difference here, I use a set instead of a list. So you could have written as a general function, give list and set in there as a function. That also would work. And then I calculate the ratio between both, and then I have a function, again, that's doing some plotting and some calculation of these things. And now I create this table here. When you see the different sizes, this is an n. The n is growing. And then you see the search time in a list and the search time in a set, and the ratio of both. And if it's 10, my set is twice as fast. If I go up to 10 million, it's 62,000 times as fast in this case. So your numbers might be a bit different, but the order of magnitude should be the same. Yeah? Because set uses a hash table in the background, or some algorithms, very similar dictionaries to look it up where the list has to go through the whole list. Yeah. Yeah. The default timer is especially designed for timing. Datetime now gives you a timestamp. Datetime now gives you a date object. You don't want a date object here. This is just seconds.
But is it like accuracy, is it the same or do you think?
Probably datetime now is using something similar behind the scene. But timeit is designed for time measurements, where datetime now is if you want to do calculation with datetime objects. In the end, they might use the same algorithm, I don't know. Actually, now in Python 3, you can use perf time, and you can use even the nanosecond version, NS, which is new in Python 3.7. Yeah. So if you don't have to use all the versions of Python, you can use a more accurate one, actually. Yeah. So, but here for this one is good enough because these differences are so big. So totally absolute. If there will be some mistake in my measurements, but if you have a factor of 60,000 times, then it doesn't matter too much. And if it's 55,000 times or 65,000 times, it doesn't matter too much. It's a big, big difference between both. Yeah, and that's just this lookup. So this is something very basic. And the same will be true for a dictionary. But if you only need keys and no values, then you should use a set, not a dictionary. Yeah, so a dictionary uses more memory. So this comes with a set needs more memory than a list. So you pay with memory. You pay with something. But typically, you can put quite a bit more memory in a machine, but you cannot make your CPU 60,000 times faster. That's impossible. But say, okay, I triple my memory, or there's no big deal. Yeah, so a dictionary takes about more or less, if you only use a dictionary with the list elements as keys, then like the factor of 4 or something, more or less. Yeah? Even though the new dictionaries in Python 3.6, they are more efficient. They lose like 20% less memory. Good. You pay something, but typically it's a small price for a lot of speed up. If you use it, it's just an example. So this is a data structure that's built into Python, and you can use it and you can make your things faster if you have this thing. If you do only one lookup, when you convert your list into memory, into a set, then it doesn't help too much. So let's look at my example I have here. So did I take my... So, yeah, of course, this is true. So I have this multiple here. This is the next one. Yeah. So I'm doing this multiple. And I go repeated times, so I can repeat it 7 times here and do the calculation again. Yeah, so I do it just like time it, and I repeat it 7 times and get the average number, and I repeat it, and this takes much longer, takes 7 times as long. Now it creates a table. Since it takes a bit here, I'm still working on it. Yeah, and then you will see that those readings might get a bit different. So if you repeat something multiple times, then you might get some more different readings here. I'm not sure if there's different readings. So you have to wait a bit. Okay, this will take a while, and we can go to the next function. I don't know if it works. Load, searching. Magic.py. So that loads a while. So now I use the timeit. I use timeit, and I can essentially recreated this %timeit from the notebook. But you can actually use the built-in %timeit from the notebook to run it. So I need to. This will go. You can look at that. This will the timings will be. You see already. This is. I will take a while here because I repeat it 10 times. Yeah. Is there a difference? Yeah. You see, this would be 40. Now it's 70, and so on. So there will be a difference. So we need to. So I don't have too much time here. I just say kernel interrupt and then. Okay, one more, 700 versus up here 200. So there are some differences. If you repeat it 7 times, you get a bit different readings. Yeah, so my 1 time is not good enough. So 7 times is better. And therefore I use magic, and this magic is using the built-in percent time it, and you can use it in your code without being the notebook if you want. You can use it in your code without being one more and then we are through. No, 10 million. Yeah, we see now this is 100,000 is now 7,000, and here it used to be only 700, so it's a factor of 10 difference. Yeah, so since my lookup in my set is so fast that my measurement is doing this. I say now because so long we have to. It's good now. The last one. Yeah, so I killed my kernel, and I load this one. You see now I'm using IPython. You can actually do this. You have to look it up in the documentation. And now my implementation becomes much shorter. When you see here, this is pretty much the timeit command with these options, and it just creates a string that's called the timeit command. So I can use all this functionality from IPython without doing the looping and everything myself. Yeah, and then I can do the setup code as a string and the statement as a string and run it to this function and do this calculation at this place. Yeah. So and then I can reuse the timeit magic without implementing it itself. So I find it pretty interesting if you want to. But you have to feed it a string, because in the notebook you type it in and it takes the source code. You have to supply the source code. But you could also read it from somewhere if I want to make it more. Now if I run this one, I can use the average, yeah, for my object. Remember, we did this before, and then you get this. What happened here? My nice example broke. Did they change something? Oh. Oh, that doesn't look nice. There's a number somewhere, but somehow there's a.
Is it like color coded?
Yes, this looks like some kind of some representation of something comes out. The numbers are there, but there's something here, and it hasn't been there before. They must have changed something by the returns, so I have to figure this out. Yeah, but you see, this gives you this numbers there. So I have to. That's broken. I need to fix it. Huh. Sorry, I have to mix it up. But it goes to the end. So somehow there's something returned. The numbers are there, but it returns something which it didn't before. There's some artifact of the. Probably I need to use the option. I use the option quiet. You see, this one's not supposed to return the Simpson. Seems like it doesn't work. I don't know. Okay. Load repeated, so just to see that you can create some of these tools here, and then you can create your source code here. I use text wrap indent, otherwise the indentation would be there, and then I can do this repeated times and then get my output, and it has the same effect now. Okay. Yeah, so I have to fix it. I don't know where it comes from. This is just some output kind of thing. And this will take a while because now it does multiple repetitions and so on. Good. So now, but it might take too long, so I have to. Kill this one. So with this kernel interrupt, you can stop this one. Okay. Another one about some simple thing that you can do with a set. Intersection is something you can do with a set. So I wrote my own kind of naive intersection with two lists. So I have two lists here, and I go through all elements of the first list, and then in the inner loop, if X is contained in the other list, I append it. So that's my intersection. And when you do this, and then you do this with the intersection of two sets, and you compare the results, then you see this intersection will be much faster. That's what it's good for. And you see if I run it here for different sizes, I get ratios. Yeah. Okay, sorry, intersection. I'm doing searching, and now, okay, that's the effect. Actually, I'm doing the searching. But I also take into account, I need to convert my list into a set to do this. You see, this is a different difference here. There's a difference. There's a difference. Yeah, this is the. There's a difference. What I'm doing. Because now you see you gain something here, but it's not nearly as much because I also calculate creation of the data structure. So if I take the creation of the data structure into account, to actually generate the list and generate the set, then the situation is different. If it's there already, it's a no-brainer. Use it. You can gain a lot. If you need to create it, then the creation time is it's very big compared to the actually time I'm working on it. So if you have a list in the first place, you need to convert your list to a set. It might not get faster if you do this thing only once. Yeah. So in general, using a set is much faster. But if you need to convert the list into a set just for one action, it might not be worth it. And again, this depends on the size of the list. If you do different sizes of list, you might get different ratios, different results. So in general, things are true. Set is much faster. But if you have different constraints around it, it might not be so big a difference, and you might not see that much here, and you can won't gain that much as a thing. Good. This would be the data structure used built-in set. There are also other data structures that are not as common. Anybody knows a DAG, a double-ended queue? So this is a different data structure which is not used that much, and this is interesting because a list is very efficient if you append, but very inefficient if you insert in the beginning. So a list only allows you adding things from the right in an efficient way. A DAG allows you to add things from the left and the right. So much better. But when you use a DAG, you cannot access elements in the middle. You only can access elements from the end as it is. And there's always, if you have something that's much better, there's some disadvantage somewhere else very often. So for some things, the DAG is much better. For other things, it's much worse. So let's do a quick example. So I have so it's in the collections module, which is a module that gives you some extra data structures. So for more than 90% of the cases, you will be totally fine with lists, sets, and dictionaries. But sometimes you want to reach to collections. There's a counter. So a counter is probably not faster than doing it yourself with a list, but it's more convenient, typically. There's a name tuple, and there's a collections DAG here. Double-ended queue. Oh, takes a while. And now I have it imported. And if I make a list L, this has a certain size. Here, I can say, my list looks like this. So, list. Yeah. And now, a list looks like this. And now, if I would like to delete the elements 2 and 3, so 2 to 4, exclusive, I can just assign an empty list. This would be a way to delete these 2 elements, remove the elements. Yeah. If I do this with my DAG, things are different. So the DAG, you cannot just go in and delete things, but what I can do, I can say, DAG looks like this. I can say rotate, so I need to rotate, and I rotate by -4, then my DAG looks like this, you see, it's rotated around. And now I can remove things either from left or from right. So I can say deck pop. It also has a pop left. So the Python list only has a pop from the end. In here, okay, you come pop from there, which removes the 3. And now I can also say pop again, which removes the 2. And now I can rotate it back, and I have the node, now because I moved 2, I say rotate 2 in the other direction, which gives me back this one. Yeah, so we start with a list, and then I remove the elements. We start with a deck, and I can do this. But I have to do more steps. The list is 1 line. Here I have to do 3 steps. So it's more effort. Yeah? So you can do something like this, and you can rotate it back. So let's look at this one, list versus deck, a small sample function that I wrote here. It's doing exactly this. And I do multiple measurements. Again, I use a function that takes a function and a bunch of arguments. Actually, again, my repeat 7 again and my limit. This one collects all the, it takes a while, let's let it run. In the meantime, I can talk. Collects all the results, and then I say, okay, while the duration is less than limit, similar to what we have, I get my arguments here, I do my timestamp, I call my function, and then I get the increment here, and then I divide the whole duration by the count to get it per run, and then I return the mean, actually, in this case. So this is a measurement function, and this is my simple list version we just did, and this is a deck version, so it's more complicated. 1 line versus 1, 2, 3, 4 lines. So it makes it more complicated. But now I do this and I run it for different results. This is just the formatting code to run everything, and that's the output. So depending on this limit here, that's a list and a deck. You see, if I do this and I replace 1 element, my deck is 70 times faster than my list. Well, makes sense. If it's for 10, it's still 50 times faster. If I do it 1,000 times, and you see I have to say pop, 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 pop 1,000 times. And now my gains get less. And if you do it 100,000 times, it's worse. So it's not that clear. Depends on your data. If you remove only 1 or 2 elements, this deck is much, much better. If you remove a lot, it's worse. Yeah. So now you do it for different sizes here and stuff. Then you see it shows the same pattern. The numbers are a bit different, but it's the same pattern. You start off very well with just removing 1. As soon as you remove a lot, then you lose something. So you need to measure, and you have to measure for your data, and not only for the size of data, but also for the arrangement of the data. How many do you want to remove? And things might change. So you might make it 4 times as long, and in the end you'll be slower because you remove a lot. And this is still a very simple toy example. In a real program, you might not even recognize a pattern there. Yeah? If you use a lot of different data for your measurements, then you might see this result. You might not know what the reason is. Yeah, here I know the reason because I put it in, and I fabricated this example so I can explain it. In a real program, you might see these numbers, and you might see the input, but you don't know how this input produces these numbers. That's something you need to find out. Yeah? Good. Again, it takes too long. I kill this one here and interrupt. So this is just an example. So if you change the structure, and here it's quite a bit of investment because I use not a standard, not a built-in data structure. I use one from collections and replace my list with it, and it can be useful for certain types of operations. Good. There are more data structures. The next one is default dict. So again, this can be helpful, default dict, but we'll see default dict is more a matter of convenience and performance. So you don't need default dict, you can always do it yourself, but sometimes default dict can be useful. So if you want to count something like this, like this is an example. I have a string with some letters. But there's a counter, but it's a nice example. So you could do something like this. You can say, okay, my dictionary is an empty dictionary, and you can go through here and you say for key in S dictionary set default. The set default is just a normal function. You can say set default key 0, and then you can say dictionary key plus equals 1. Yeah. Which gives you a dictionary plus equals 1, no space. Dictionary that looks like this. It calculates how many times each letter. You can use counter, that's even faster, but as an example. But you could also use my dictionary 2 is default ticked, and you give it a kind of a constructor. So if the key is missing, it will use this function int in this case. So yeah, if you call int, it's not a function, it's a constructor, but it looks like a function, then you get a 0. Yeah? It has to be callable. So in Python you have a notion of callable, and of course it can be a function, and the class is also callable. So when you make an instance of a class, it's the same in syntax as calling a function. So technically something totally different, but for practical things, you just call something, you get something back. And it doesn't matter if it's a function or a class, who cares? As long as you get something back, that's fine. So you can do something like this, and now you can make this easier. I make the default dict, and then the default dict will be called, and I can say for key in S D2 key plus equals 1. So you don't have to do this extra step, they set default, and you can do this, and now D2 looks exactly the same as D. Yeah? It's a default dict, it's not a dict, but you can convert it to a dictionary in here if you do something like this. Yeah? Okay, makes it more convenient for something, because you don't have to do this extra step, and it might make it a bit faster, but not that much. So let's look at example, set default dict. Yeah, so I do the same thing, this code. Okay, could have copied from there. And then I compare the runtimes. Here, if you have, this is set default with an empty list, and append to the list immediately, which is also short here. And once you do this, now you can actually time those things, and you can say time it. And you can say so it doesn't, the call tips don't work. I don't know what's wrong with my notebook. It's supposed to work here. So if I do this here, then I get this one, and if I set as a default dict, and then you might get some different timings. Yeah? You can measure. There are some small difference, but S is very small. If you have a bigger one, there might be some difference anyway. So it's more convenient typically to use default dict, but the time gain is small, at least for my example. Again, now you can do the fun, use the size what you want, and you can see it. So it's more convenient, but at least it doesn't get slower. Sometimes more convenient, it might get much slower because it's doing a lot of extra things. It doesn't. It's a bit faster in this case. It also might depend how often this int is called, because calling something in Python can be slow compared to some other options, and depends on the structure how often these things are missing in there, and this int is called, and not. Okay. Oh, time's over. Good. Yeah, we are nearly through here. These are just a few examples. So as you see, time-wise, we cannot cover much more. You can do a lot of more things. One quick thing: if you look at page 67, there's this about big O notation. which is typically a measure how long things take when you do something. So O1 means it doesn't matter how big your structure is, the time is always the same. If I say length of something in Python, it doesn't matter if it's a length 10 or length 10 trillion. This is pre-computed already, you just retrieve the length. You don't count anything. That's O1. On means it depends on the size. So if you make a list 10 times as long, it takes 10, instead of 10 elements, 100, it takes about 10 times as long to go through the list if you iterate through. That would be O1. And then there's quadratic. So if you have a loop, go through the list and then go to each element, that would be quadratic. That's O. Typically, that's what this big O notation says. And I have some examples, what kind of algorithms have what kind of, it's just big order of magnitude things. There's nothing very, very fine, but typically it's a good idea, it's good to have some idea what kind of a notation you have. Like looking up some things in a set and looking things up in a dictionary is O1. It doesn't matter if the dictionary has one element or many elements at the same time. If you do the same thing for a list, typically it's linear, and if a list gets bigger, then things take longer. We've seen this with an example, and this is just a formalized way of doing this with a big O notation. And I have a few examples here again with a big O notation in this case. Good. Pretty much true. There's one last small topic, caching, but this is just another thing. If you don't recompute something, probably we can skip it. And there's another short table about some libraries that can make you things faster, mainly focused on numerical algorithms, but I think it's maybe not so. I think we only have 3 minutes left. That's why I would stop here. We made most of it out of 70 pages in 3 hours. That's not too bad. I hope you learned something. So this is something about principles. So measure, measure, measure. Write some tools. Use existing libraries that help you to measure. Integrate them in your tools and decorators and other things to try to automate as much as you can. And as you see, I made some tables, and it's helpful. You spend an hour to write a tool that makes a nice table, but they can rerun it again, and you see the table immediately. Otherwise, if you have to look through numbers, you won't miss something. Yeah? Make a table, make a graph, do some kind of tools, and measure something. And again, use algorithms to make things faster before you think about rewriting stuff in C or other languages, which can be a major effort. Okay, probably have to optimize my speed a little bit. Hopefully I was not too fast. I hope you learned something. Thank you very much. Again, go to this link here to do this evaluation. Of course, I've forgotten to upload it, but I put it in here, so it's somewhere here. If you go to the link and evaluate. Otherwise, thank you very much, and have a good time at the conference. So this concludes the tutorial days. There's a reception tonight, and tomorrow and the next 3 days there are talks, and then next week there are sprints, which is pretty interesting. And this would be the link to the evaluation. Thank you very much.